Okay, welcome back. Let's get into distribution system math part 3. We're going to get into pounds and the strength of some of these chemicals and how we're going to dose it into the water. So we're going to disinfect water storage tanks. We're going to disinfect water mains. We got to figure out the volume in gallons. And we're going to use something known as the Davidson's pie chart to help us with this. So the formula sheet, page 3 of 8, as at the bottom shows that there's this feed rate pounds per day formula. And the formula reads like this: feed rate pounds per day is equivalent to the dosage as milligrams per liter. Remember, this could also be ppm, by the way. And the flow rate has to be in million gallon units or million gallon a day units. And we have to have 8.34 pounds per gallon. That's our conversion to go from pounds of chemicals or gallons into pounds. So we're going to use this thing called the Davidson's pie chart, and I'll show you how to use this here shortly. The thing to know is that whenever you're working with Davidson's pie chart and you have numbers that, so to speak, fill in these little pieces of the puzzle, they're always multiplied together before we do anything else. So in this case, if we have three values plugged in, if we have a flow number and we know the dosage number, and we always know 8.34 because that's a constant, we always multiply those numbers together. So we have several multiplications to do, and that answer will come out to be the pounds per day of the chemical. Now, if it's 100% chemical, like chlorine gas is, then we are good to go. That's the answer. That's the final answer. We don't have to do anything else. If we're going to be dealing with a weaker chemical like sodium hypochlorite, which is bleach, or we're using calcium hypochlorite, which is HDH, and they're not as strong as gas chlorine, we're going to have to do a little bit of extra work because we're going to need more of that chemical to do the same job. So let's go ahead and dive into this and see how it goes. So first question says, how many pounds of 100% chlorine will be needed to disinfect a storage tank that contains 750,000 gallons of water to a dosage of 50 milligrams per liter? So we can use this Davidson pie chart to help us out. We can plug numbers in. We've already got 8.34 here. This is pounds per gallon of water weight. And we know that the concentration, or in this case, the dose, is 50 milligrams per liter. But what about the water content? You know, we have 750,000 gallons showing, and it's not in million gallon units. So don't forget to divide the 750,000, divide that by 1 million to come up with the right million gallon equivalent. So 750,000 gallons divided by 1 million gal per mg is going to end up being 0.75 million gallons. So we have 0.75 million gallons. So that number is going to plug in here. And I put the 0 there to show you it's the number is whole. It's less than 1 whole million gallon. It's 0.75 million gallons. So now we have our factors. We can go ahead and plug these numbers in and do the math. So 0.75, remember, multiply by 50 by 8.34. And for pounds formula at the top, we have pounds is 312.75. And since we don't have day units attached to the flow, this is just gallons rather, it's not a million gallons a day, the answer actually is just pounds. We don't carry the day units into this one. So the way we would write this, if we were just to use the formula without the Davidson pie chart, would be the pounds equals the flow rate, which is 0.75 million gallons, multiplied by the concentration, or the dose, which is 50, and in this case, milligrams per liter is the units given. And then we know 8.34 pounds per gallon, and that's how we would write it out. So it's multiplying all three digits together, all three values together, and we come up with 312.75 pounds of 100% chemical. All right, let's take a look here. So what about a storage tank? If we were going to disinfect a storage tank that we didn't get the gallons, or we didn't get the actual, million gallon number, what if we had to figure it out? Which is probably similar to what might happen like on quizzes and questions and, final exams and exams just in general, right? So we have a water storage tank that's 30 feet high. We have a 120 foot diameter for the water storage tank. So we know it's a circular shape because the word diameter is given. And we're going to dose it to 50 parts per million. So the first thing we need to do is remember that we can use the Davidson's pie chart as a visual image if you wanted to remember that. So we have 8.34, and remember that that's pounds per gallon. And then we need a concentration of something. The concentration, it goes here. So we're going to say 50 ppm there. And then we need to figure out this part. This is what we're trying to figure out right now, is what are the million gallon units? So let's take a look and see how we do this. I think there's a tutorial coming up next, but we're going to kind of work it out on the screen here. So remember that we have a diameter given, so it's a circular shape, and we need to figure out the gallons in that circular shape. So we're going to use 0.785, and I'm using that number because diameter is directly given. So I have 120 foot diameter times 120 foot diameter. And then the height of the tank is 30 feet. And let's go ahead and see how many cubic feet this turns out to be inside that vessel or that tank. So 0.785 times 120 times 120 times 30. And I came up with 339,120 cubic feet. All right, so that's one step out of the way. We know how many cubic feet. Now we need to multiply by the amount of gallons in a cubic foot to get it into gallons. So 339,120 cubic feet times 7.48 gal per cubic foot. All right, so work calculator has our value in it here. So times 7.48. And I came up with 2,536,617.6 gal. And that's just number of gallons. That's the raw gallons. That's still not the right units. It's not million gallons at this point. We need it to be in million gallon units. So we divide this by 1 million to put it in the right units. So we end up with 2.5366176. So that's a lot of numbers. That's a lot of digits. We don't have to carry all those digits into the pie chart or into the calculation. Let's go ahead and drop off some of these numbers and round this off. So how about we drop off the 6176 and round this to an answer of 2.537. And if you guys agree to that, I'm going to plug that number in right here. 2.537 million gallons. And now we just do our pounds formula. 2.537 times 50 times 8.34. And I came up with 1,057.929 pounds of chemical. And for purposes of this math, let's go ahead and just round it off and just say, how about this number? 1,058 pounds of chlorine are needed. So that's our finished answer for this question. 1,058 pounds. We're just multiplying the numbers on the bottom of the pie chart together. We said anything on the bottom always gets multiplied together first, and we end up with the pounds left over, or as the units left. So let's see how our tutorial tells us if we hit the mark on this one. So we calculated out the cubic feet. So we have that correct. That checks out. And we have the cubic feet into gallons. Now we have to multiply that by 7.48. And that's also what we had on the previous slide. So that looks pretty good so far. Don't forget that has to be converted into million gallon units. So I'm moving forward with this. Here's our rounded off version of the million gallons. So far, so good. Now we plug these numbers into the Davidson's pie chart, and we should have everything we need. So we're going to use the pounds formula now. So we have the milligrams per liter. We know that was 50, and we know the million gallons is 2.537. And now we do our multiplication, and let's see how we did. We got our numbers plugged into Davidson's pie chart. Here's this number. We're multiplying times 50, and we're multiplying again times 8.34. And then our answer comes out to be 1,058 pounds of chlorine. There you go. So that's how we work the math out using the pounds formula and the Davidson's pie chart. Now, because we're not dealing with gaseous chlorine and we're trying to get away from carrying large amounts of a hazardous chemical, we're using chemicals a little bit safer to handle and a little bit more easier to apply. So let's talk about the calcium hypochlorite and the sodium hypochlorite, which is essentially known as industrial strength bleach. So a classic example for us is to use something like we're going to disinfect a pipe. How many pounds of calcium hypochlorite might be needed to disinfect a pipeline? You know, we put a new water main in the ground, and now we have to disinfect it. So now we're going to work on how to calculate the pounds of chemical needed for that. Remember that the alternate chemicals are not as strong as the 100% real stuff. So imagine, if you will, that we're going to need a little bit more of that chemical to do the same job, killing the pathogens or the bacteria that might be lurking inside those water pipes. So we have 100% chlorine here in 150-pound cylinders. We have bleach that comes in drums or containers that can hold this. You can get this from swimming pool supply stores. It has to be NSF certified. That's the only thing here for us with water treatment. We have to have an NSF certification on it. That's National Sanitation Foundation certification. And you could use bleach, which is around 12 to 15% chlorine. Or you could switch to the calcium hypochlorite, which I show here is about 65% or higher chlorine value, trade strength value. So that's all this slide is telling us, you know, the different trade strengths on the chemical. The main thing I want you to know is that bleach or sodium hypochlorite is a liquid, and the calcium hypochlorite that we're using is going to be a powder or a solid chemical. So calcium hypochlorite is typically measured as pounds, but sodium hypochlorite is typically measured as gallons. And that's where the big difference is. We have to kind of pay attention to what chemical we're using, if it's dry or liquid. So our formula sheets do show us how to work this out. The thing you have to know first is you got to do the 100% version of it. And then what we're going to do is divide by whatever strength they tell us, whatever chemical they tell us. If you have this at your warehouse or your supply trucks or whatever, you know, it depends on what chemical you're using. So the first things first is to figure out the 100% chemical, how many pounds, and then go from there if it's calcium hypochlorite or HDH, or if it's actually going to be bleach, you know, the liquid. So that's where these two formulas come into play. If it's pounds or it's a dry chemical, then you're using this one. If you're using a liquid, you have an extra step to do. Okay, you'll notice here. So let's go ahead and work this out. So percent trade strength is what we're talking about. And to get the pounds of the chemical needed, they're going to tell you, or you're going to see on the label, a percent strength. So how do you get that into a decimal equivalent? So let's just say that, they told us it was 65% available chlorine. So we do a division. We divide 65%, divide the number by 100. And what it does is it gives us a number that looks something like this on our calculator. We move the decimal point 2 places over, or the decimal point appears 2 places over, and that's the decimal equivalent for 65%. If it was 12% bleach and you had 12% bleach that you're using, it's the same formula. It would be 12%, just 12 divided by 100 gives us an answer of 0.12. So those are decimal equivalents. If you're using the bleach, the liquid version of it, then we have one more step to do. The bleach pounds then gets converted to gallons by dividing by 8.34. So for formula purposes, for formula sheet purposes, they have 8.34 on their formula sheet. In the real world, bleach is heavier than 8.34 pounds per gallon. And if you know the equivalent weight in pounds per gallon, then use what you have on the label. If you don't know and you're just going to guess, well, then you're going to use 8.34 if it's a liquid, okay? So let's take a look. We got some examples here. We have a high strength or a percent strength example. We're going to use the HTH. The HTH is calcium hypochlorite. It's the dry chemical. So what we're trying to figure out is how many pounds of dry chemical. We have some known values. We're treating 10,000 gallons in a pipe. The dosage is going to be 50 milligrams per liter. That's a general number that we use when we disinfect water mains. It's a pretty strong dose. That's a really high amount of chemical to kill bacteria that could be inside that pipe. And the chemical we're using, it contains 65% available chlorine. So first things first, we need to figure out what the 10,000 gallons are as million gallon units. Remember, using the Davidson's pie chart to help us with this. So we have to configure this gallons into million gallon purpose or number. So 10,000 gallons, 10,000, divide that by, here's our 1,000 gallons per million gallon number, divide by a million. And I've got 0.01 as my million gallon number. Pretty good so far, hopefully. So there we go. We have 0.01 mg for the liquid version. So now we go to our pounds formula. You can use the Davidson pie chart, or you can use like I'm showing you here. So we've got 0.01 mg. Actually just going to be million gallons because it's not really moving through the pipe. So we're not going to worry too much about the day units here. And we have our dosage. This could be milligrams per liter. It could be parts per million. Doesn't really matter. And we have 8.34 here. So you're just multiplying the three numbers together. So put them in as you're shown here. So 0.01 times 50 times 8.34. So for this part of the calculation, I came up with 4.17 pounds of actual 100% real chlorine that would be necessary to do the job of disinfecting 10,000 gallons of water main to a 50 part per million dose. So that's how many pounds of 100% real chlorine. But we're not using 100% real chlorine. The question told us that we were using 65% available dry chemical known as HTH. So let's go to the next slide. So we had 4.17 pounds of 100% chemical, and now the formula tells us to divide it by the trade strength written as a decimal. So you see here 0.65 is given. Remember what it was it was 65% available chemical. So the 0.65 is that converted into a decimal. So 4.17 divided by 0.67. And now I came up with let's go to 6.22 pounds of HTH. So that's how much HTH would be needed at 65% available chlorine to reach the 50 part per million dose. And notice that the pounds of the chemical, because it's weaker, we need more of it than what the initial 100% chemical was. This is 100% here, and we're not using it as 100%. We're using a weaker version, so we need more of it. if you were to make a mistake and calculate this as a multiplication rather than a division, and you were starting off with 4.17 and multiplied it by 0.65, you actually come up with a number that's significantly less than the 4.17. This would be 2.7 pounds of HTH, and you would not meet the 50 part per million dose. You would be way under the 50 part per million dose, and you may have coliform positive bacteria out after this has been sitting for 24 hours and you flush it. You may not have killed everything that you were trying to kill. So this would be an underdose situation. So don't do that. You have to follow the math as it shows. It's the division of 0.65, not multiplication. All right, so hopefully that's sinking in and you're seeing what the concept is here. So we have a drum here, 100 pounds of dry granular chlorine used for disinfection. All right, let's go to the next slide. This is using the 15% bleach, or let's say a weaker strength bleach as a liquid. So what we're going to now figure out is how many gallons of the bleach. This is not just dry chemical. This is now a liquid. So we're going to treat 30,000 gallons in a pipeline. It doesn't matter what diameter it is. It doesn't matter how long it is. We already know it's 30,000 gallons that we're trying to treat. We're going to dose this again at 50 milligrams per liter, and we're using 15% bleach. The question's asking us how many gallons would be needed of this bleach to achieve this dose. That's the key factor. We need that dose. So first things first, 30,000 gallons in the pipeline doesn't fit the pie chart, doesn't fit the formula. Remember, we're trying to go to million gallon units. So first steps first, convert the 30,000 gallons into million gallon units. So 30,000 gal divided by 1 million gal per mg, that's my units, was going to give me 0.03 million gallons. On your calculator, you should be seeing 0.03 at this point. So if you're good with that, we'll go to the next slide. But that's the number we got to carry into the pounds formula. All right, so here's that number carried into there. There's the 0.03 mg. This is just going to be million gallons because remember, it's just a pipeline laying there. We're not feeding it in a matter of a whole day. It's just going to be a dose. So we're not going to worry about the day units on this. It's just million gallons. So 0.03 times 50 times 8.34. So that times 50 times 8.34. So I came up with, in this case, 12.51 pounds of chemical. Now notice it's significantly more than the previous example because now we're dosing 30,000 gallons instead of 10,000 gallons. And the dosage is still the same as far as 50 milligrams per liter, but it's a lot more volume. So 12.51 pounds of 100% chlorine are needed. So we carry that number into our next slide. Here's the 12.51 pounds. Now remember, it was 15% available chlorine. So 15% as sodium hypochlorite is now equivalent to 0.15 written as a decimal. So that's what we have here. So 0.15 decimal of solution. The solution is the liquid part. So 12.51 divided by 0.15, and I came up with 83.4 pounds of the chemical as a dry weight. Right now, we have not converted anything into gallons yet because we haven't used 8.34 or any other weight of the chemical. We're just looking at the pounds as if it was like HTH that was only 15% available chlorine. If you bought HTH and it was only 15%, you'd need 83 pounds, which is a lot of pounds when you consider, the strength of the chemicals with HTH is usually around 65%. It was a lot less pounds when we were using 65%. So we're not quite done yet. We got 8.3 or 83.4 pounds as dry weight. And now we populate the slide down here. We can say 83 83.4 pounds here. I'm going to write that number in here, 83.4 pounds. And what we're going to do is we're going to divide it by the pounds per gallon. It's just a coincidence that it worked out this way. And I wasn't planning for any of this kind of stuff to show, like these numbers to look so similar. It's purely a coincidence because we didn't plan for it. But 83.4 pounds as a dry weight divided by 8.34 pounds in a gallon. And I came up with an exact number, which is interesting, an exact number of 10 gallons of 15% solution, which is the sodium NaOCl solution. So 15% solution, we'd need 10 gallons of that. So that's how we would do the math using a weaker chemical, and in this case, a liquid chemical. Now, if you know how many pounds per gallon your chemical is, if you know that you have sodium hypochlorite and the sodium hypochlorite you have is, let's say it's 11 pounds per gallon or 9.5 pounds per gallon, whatever that number is, you would use that number here instead of the 8.34 that I used. If it was, say, 9.5 pounds per gallon, then we would substitute that right here, and you would factor that in. You'd figure this as, so 83.4 divided by 9.5, and you'd come up with an answer then of 8.77. So let's go 8.8 gallons of 15%, because you need less of it because it's a heavier chemical. So it's a little bit more dense. So that's how we'd work that out. If you have a number that works at your plant, if you have the actual pounds per gallon, then use that by all means. If you don't know the number, then use 8.34. You'll actually put a little bit more in than maybe required, but you will still get the 50 part per million dose, maybe a little higher than the 50 part per million. You won't be underdosing it. So I hope that's helpful. Let's talk about the dosage of chlorine, or the dosage of a chemical. Let's investigate this Davidson pie chart a little further. Let's talk about how we can actually utilize the Davidson pie chart to help us here. So we had this circle a little bit earlier showing on the screen, and it had these little quadrants, these little pieces of a pie underneath. And you'll remember that we had pounds of chemical here, and we had 8.34 showing here. That was pounds per gallon. And then I usually put my million gallons here, and then down here I have milligrams per liter. So what we're trying to figure out with an equation called dosage is we're trying to figure out actually what is the milligrams per liter. That's the missing piece of the puzzle in a question like this. So you're trying to figure out actually what is the ppm or what is the milligrams per liter. That's all we're trying to figure out. So what we're going to do is we're going to use the Davidson pie chart to help us out. And remember that any numbers that get populated into the southern hemisphere of the pie chart are always multiplied together first. So if I have some number here, and let's say that that is some number, double-digit number, and we're trying to figure out what the milligrams per liter is, we still multiply the million gallon numbers by 8.34. We still do that. And then we take that value, we take that factor that we got, and it's going to be over here as some number, and it's going to be divided into the pounds that we're going to be given. We're going to know what the pounds is from a scenario. So then we'll come up with the actual milligrams per liter number. So let's work a few of these out, and I'll show you how this works. It's pretty straightforward. The values are shown here. The water volume as million gallons is multiplied by 8.34 and then into the pounds of chemical. That's how I show it. And again, like I said, there's multiple ways that you can come up with the same answer. You don't have to do it exactly as I'm showing, but I'm going to kind of point it out or guide you in the direction that I think works pretty well for us. So the Davidson pie chart helps us with the calculation, and we're trying to figure out the pounds, or rather the parts per million or milligrams per liter. All right, so here we have the first question. The operator has fed 113 pounds of chlorine into a daily flow of water, and the daily flow was 1.5 million gallons per day. So the question is asking us, what is the actual chlorine dosage? And the chlorine dosage is either milligrams per liter or ppm. We're trying to figure out either one of those. That's kind of the hidden thing we're trying to find. So let's work this out. We got pounds of chemical. We know pounds of chemical is 113. And we know the water volume in this case is already given to us as million gallons a day. So there we can just plug that number directly in, and we have our numbers already figured out. If we're going to use the Davidson's pie chart, we're going to kind of write it out. Let me see. I thought I had that written out for you here. We're going to write it out like this. Kind of draw one of these out. I think it might be on the next slide, but that's okay. We'll go work it out here. So we got our pounds of chemical, 113. This is pounds per day. And we treated 1.5 million gallons a day. And our number that we're trying to solve is right here. This is the ppm. And we always know 8.34. Again, our friendly constant that's with us on this is 8.34. We always know that that's in there. So remember, multiply the two numbers together first on the bottom half. So let's take a look. So we've got multiply the denominator values. We said 1.5 times 8.34. What does that come out to be? 1.5 times 8.34. We got 12.51 as my denominator. So now we're going to divide the pounds of the chemical by that water weight, which is 12.51. So 113 divided by 12.51, and I'm coming up with 9.03 parts per million. 9.03. That's a zero there. And we got 9.03. I rounded here, so we just knocked off a lot of the digits off of this, but 9.03 part per million is our dosage. A way that you could check yourself to see if you really did the math correctly is by kind of finagling the Davidson pie chart a little bit. Let's move this out of the way here real quick. You could kind of work this pie chart to your favor if you remember something about it. Anytime that you have numbers on the bottom of the Davidson pie chart, you always multiply them together, and you should end up with something close to the pounds of chemical per day, which is what you end up figuring out when you multiply by them. So 8.34, it kind of lives here. And we said 9.03 ppm there. And over here, we're going to put our flow. We said 1.5. So let's just try it out and see if it works. Multiply the numbers on the bottom together first. 1.5 times 9.03 times 8.34. I came up with 112.9653 is the number I got here. And guess what? Rounded off, that would be 113 pounds. So we did good. This number 9.03 is a good number that will work for us. So we did the number, we did the math correctly. We came up with the right number. All right. So how about we try this one out? A contractor has calculated that 6.5 pounds of chlorine are needed to disinfect a new 12-inch water main that contains about 15,500 gallons of water. What dosage of chlorine will be met? So what will the dosage be if we used these numbers? So what we're going to do is kind of check and see, is the contractor going to get us to that 50 part per million dose if that's what we're trying to get? Let's just see how this would work. So I think we have a Davidson pie chart we could use for this. I'm going to kind of, just as a reminder for you all, just remember what we're trying to solve here is this middle piece. What dosage will be met? And we have 6.5 as our numerator, and we know that 15,500 gallons are used, but we have to convert that into million gallon units first. We certainly can't use the 15,500 as a straight number. So let's convert this 15,500 first into million gallon units. So 15,500 gal divide by 1 million gallons per million gallon units. So 15,500, and we divide that by a million. And I came up with 0.015. All right, so that's pretty good so far. And we always know 8.34. And I always put it over here, but you can put it in the segment right next to it if you wanted to, next to the flow. Either way will work. So 0.015 multiplied by 8.34. And I've got a factor, a bottom factor here of 0.1251. And we're going to divide that into the 6.5 pounds that was going to be used. So 6.5 divided by 0.1251. And I'm coming up with 51.96, which is actually over the 50 part per million number that we were hoping for. So it looks like in this particular case, the contractor would be using enough chlorine to meet the 50 part per million dose. So we're going to be slightly over, which is okay. So let me see how we did here. I think we have the tutorial here. Let's see what we did. Step 1, convert the gallons to million gallons, which we said was 0.015 mg. And now we multiply the denominator values, which was 0.0155. So we actually have 0.155 here. We put an extra 5 here just to kind of carry that over. So times 8.34. And I got 0.12927. And divide the pounds of chemical by the water weight, which we said was 6.5, divided by, let's see, we rounded again here. So 6.5 divided by 0.13. And I came up with 50 parts per million. So because this is rounded, it came up exactly as 50 parts per million. So yes, we will meet the number. In the previous little scenario I gave you, I kept the numbers a little bit more intact and we came up with the right number. So we did good. We did good. I like that. In the previous example, a dosage of 9 parts per million was achieved using 113 pounds of 100% chlorine. So that's using what if we're using 65%? So we said let's see, where did we go with this? In the previous example, that was in a previous one where we had earlier. What if we used a dosage of 9 parts per million to achieve 113 pounds of 100% chlorine? If the operator was to use 65% calcium hypochlorite, how many pounds would actually be needed? So let's just say that the operator came up with 113 pounds of chlorine that were needed to get a dosage of 9 parts per million. Let's just say, I know it says a previous example. I think that slide's a little bit out of order, but that's okay. We'll continue working with it. So we had 9 parts per million using 100 to get 113 pounds of chlorine. If the operator was to use 65% HTH, how many pounds would be needed? So we have 113 pounds. And we're using 65%, so 0.65. So how many pounds would really be needed? So 113 divided by 0.65, and I come up with 173.85 pounds of 65%. All right, so there we go. And we came up with 173.85 Got my numbers a little bit out of whack there because of the placement of it. So just want to kind of point that out there. I think that we had a little skew here on one part of it, but that's okay. We kind of knew what we were dealing with here, so we're good to go. We know the pounds and we know 65%, and the question says how many pounds do we needed. So same math, no problem. How about in this one? If in the previous example, in another example, that the operator was using or trying to get a dose of 9 parts per million, and they were using 113 pounds of chlorine. And the operator now is going to try to use 12% bleach. How many gallons of bleach would be needed? So we know that we have 113 pounds that's needed, and we're going to switch to this bleach. So let's work this out. So 113 pounds per day divided by, remember, convert this into a decimal equivalent, which is 0.12. How did we do that? It's 12% divided by 100 equals 0.12. So 113 divided by 0.12. And now I'm coming up with 941.6666. Let's go 941.67 pounds of the 12% bleach. Now this is pounds, not gallons, and we're trying to figure out gallons. So we're going to take the 900 and round it off a little bit here. We have 947. Let's just, this is actually going to be 942 pounds of chemical per day, rounded. So 947 and divide by 8.34. We're using 8.34 because we don't know the actual weight of the water, or the liquid bleach rather. So we're just using 8.34. So 942 divided by 8.34. And I came up with 112.9 gallons of 12% bleach. So where we were going with this scenario in this particular one is when you're using 12% bleach, 12% bleach using 8.34 as the division factor for pounds per gallon gives you a number like this that is very, very close to the actual starting weight that we were dealing with in the beginning of this concept. So when you're using 12% bleach and you're using 8.34 as the factor, the value comes up really, really close to the 100% chlorine that you're using. I just wanted to kind of point that out because a lot of us use 12% bleach or 12.5% bleach, and the numbers do match up really close. So that's kind of where the scenario was going on this equation or this question. So I hope that helps you guys out a little bit. It does match up pretty close to the pounds of the 100%. All right, so here's another question. The general contractor installing a new 8-inch water main that contains about 7,000 gallons of water tells you that he plans to use 4.7 pounds of 65% HTH tablets to reach the 50 part per million dose. Is this amount of HTH going to be enough? So we're going to need to know how to do the calculations that we just went through. And remember that we're using a weaker version of the chemical. So the first things first is converting, remember what we said, convert the, you can use the 65% HTH to 100% equivalent, which is what we're going to do here is going to be 0.65 as a decimal equivalent. And we're also going to be using the pounds that we already know. We know that we have 4.7 pounds of 65%, which is this. So remember the decimal equivalent is 0.65. So let's try this out. 4.75 times 0.65 gives me as an equivalent weight of gaseous chlorine, because we're actually going kind of like backwards with this math. So we're trying to figure out, is the actual number going to be enough? So we're going in a way, we're going to kind of go backwards to what 100% real chlorine would be. which is why we're multiplying it by the 0.65. So I came up with 3.0, how about we go 3.09 pounds of 100%. So we're kind of checking their math to make sure that we're going to come up with the right number. Now, if you're confused, remember what we said earlier, that gas chlorine is 100% real stuff and the HTH is weaker version of it. So if you wanted to double check this and see if this was going to be similar, if you took the 3.09 and divide by the 0.65, you come up with 4.75. So the numbers are matching up so far. So this is 100% real stuff. The 4.75 is the weaker version, but we're kind of back calculating here. So convert the gallons to million gallons. So what did we have here? We had 7,000 gallons, and we're going to divide that by the number 1 million. So I'm going to come up with 0.007 million gallons. So 7,000 in your calculator, divide by the number 1 million, and I came up with 0.007. It is important that you get the decimal point in the right spot and that you have the right amount of zeros in this. 7,000 gallons is the same as 0.007 million gallons, okay? So hopefully so far we're good. So we're going to go back now, go back to my calculation, and we're going to multiply the denominator values to see how we're doing. Remember, we're working this pounds formula kind of in reverse. We're coming up with the parts per million. So 0.07 million gallons times 8.34. And on my calculator, I came up with 0.058. And we'll just go out to I have a 0.3, I have 38 next to it, but we'll just go to 0.058. And now to finish it out, divide the pounds of chemical by the water weight. So we said 3.1 pounds because that's actually the chemical at 100%. So 3.1 pounds divided by 0.058, 3.1 pounds of 100%, divide that by 0.058. And I got 53.4 parts per million. All right, so it looks like if we back calculate and come up with these numbers, that the contractor would be using enough chemical. The 4.7 pounds of 65% would give us at least a 50 part per million dose. We have 53.4 showing here. And we have yes. So how you can prove this math, if you want to double check your work, we can do the reverse. We can kind of hit the brakes and go the forward motion. So remember that if we use the Davidson pie chart to help us with this, and you would double check your math, we can plug the numbers in as they are. So we had 53.4, we had 8.34 here, and we said the flow or the liquid was 0.007. So let's work this out and make sure we're doing it right. So 0.007 times 53.4 times 8.34. And I come up with, right now I got 3.117. So we'll just go 3.11. This is pounds of 100%. And we said that we're not using 100%, we're using 65%. So 3.11 divided by 0.65. So 3.11 divided by 0.65, and I get 4.78 pounds of 65%. So the number that we have showing up here, 4.75 pounds, is actually exceeded by them using 4.78 pounds. So it just proves that our math was correct. So yes, we are going to be good with this. Remember, this is commonly done in the field by general contractors. And it is important to us as operators that we make sure that they're dosing these things correctly. We do have to get water main clearances, which means we have to collect samples, make sure that the pathogens are inactivated. And if they are not, then we have to redo it. And if we are not dosing enough chemical to start with, we may not actually achieve the right pathogen kill. So it is important that we know how to do this. This would be a little more of a higher level math question for, let's say, a distribution level 1 or distribution level or class 3 or 4 license as you go up the ranks. But yeah, definitely something you'd want to pay attention to and know how to do. All right, so we have a couple things left to cover here with dosages and all that. So we're going to talk about what the milligram per liter demand is. We're going to talk about what the dosage, how to calculate the dosage from some known values like the residual, and we're going to talk about how to calculate residual. So that's what we have on all of these 3 lines of equations. So we could figure out any 3 of these things. We could do the demand, the dose, or the residual. We just need to know a couple of pieces of information. Formula sheets on page 3 is where this is found. So let's kind of work a couple of these out. If we know the dosage and we know the residual, now the dosage is what we just talked about. We had a couple of dosages come up. We had 4.75, we had 3.11. We had all these different numbers pop up for us a little earlier, and these were all in parts per million. Or milligrams per liter. So if we know what the dosage is and we can go out and measure a chlorine residual, we can figure out something known as demand. We can figure out what is actually consuming the chlorine inside the pipeline. That's what we're going to figure out from here. We're going to also be able to figure out the dose. We can also figure out the residual. We can figure out any part of this if we just know a few pieces of information. So here's an example. We have a chlorine residual analyzer or chlorine residual meter showing here. And we have a statement that says the operator used 5 pounds of HTH to achieve a dosage of 25 parts per million. All right, so they used a bunch of HTH and we came up with 25 ppm at the end of the pipeline. We dosed it in there a little bit higher, or rather we dosed it in at 25 ppm. And after 24 hours of standing, the chlorine residual was measured and the residual was 11 parts per million. Kind of see that here on the little chart here, little meter. So what was the demand? If we put into the water 25 parts per million and we're coming out or at the end with 11 parts per million, what is the demand? So the demand actually is written like this. It's the demand in milligrams per liter is equivalent to the dose, which is in milligrams per liter. So we said 25 ppm here, and we're going to subtract from it the actual residual. The chlorine residual left over was 11 parts per million. And remember, parts per million and milligrams per liter are the same thing. So let's just kind of clean this up a little bit. I get a little sloppy here as I'm working with this little whiteboard here. This is ppm, and this was 11 parts per million. Okay, so we're going to subtract. So subtract one from the other. So 25 minus 11. So guess what? I came up with 14 parts per million of chlorine demand. So that's what was consumed by the bacteria or the organics or whatever. That's what was destroyed out of the 25 parts per million. And we ended up with 11 part per million dose. That's how you do it. That's a pretty straightforward, pretty simple calculation if you just follow the math as it's shown. So that concludes part 3 of 7. And when you guys come back from a break, we'll be going into pressure and pounds per square inch, as you can tell by this water tower. And we got some more still to do. So hopefully you guys are hanging in and this is helpful for you guys. So I'll see you back in just a little bit. I'm going to stop the video and I'll see you on the other side of my break. All right. We are back in business. Let's get back to this math. All right. So we're on part 4 of 7. So let's continue on water distribution system math. We're going to calculate water pressure. We're going to calculate velocity. We're going to calculate flushing rates, flushing time, flow rates, all kinds of fun stuff. So first thing we got is water pressure and feet of head. This is on the formula sheet. It's page 5 of the formula sheet. We have water pressure and head showing here. So we're going to work both of these calculations, or we use several of these in this description. So first things first, what is the water pressure at the bottom of a storage tank if the tank is full and the tank is 130 feet tall and is filled to an elevation of 121 feet? So when you look at the formulas that we have here, we have two separate things written out. We have when we're dividing 121 feet by 2.31 feet per PSI, we come up with 52.4 PSI. So remember, what we're trying to do here is the PSI number is going to be a lesser number or a lower number than the actual feet of head of water above the gauge. The other way we can calculate it is by multiplying the 121 feet of water elevation by how many PSI is in each foot of water, which is 0.433. So we come up again with 52.4 PSI. If I can go back just for a second, I went over something a little quick there. Let's go back and look at this formulas on the formula sheets. I wanted to kind of point one thing out to you that I realized that maybe it might be helpful is the head of water in feet is equal to the pressure, PSI, multiplied by 2.31 feet. So we got that factor. 2.31 feet is how many feet of water per pound per square inch, or the head of water could be pressure divided by 0.433. Now remember, 0.433 is how many PSI for every 1 foot of water. So if you're trying to figure out the height of the water, it's called the head of pressure or head of feet of water above a pressure gauge. And if you're trying to figure out what the actual pressure is, then we would be wanting to know what the head of water is above that gauge. So, that's kind of where we're at with this, is the feet of water is then divided by 2.31 feet per PSI, or we have the head in feet, the elevation of the water above the gauge, multiplied by 0.433. So again, did kind of go over that. I kind of skipped over that slide there for just a second, but let's make sure that we're seeing what we're supposed to do here. So I gave you a couple of examples here. We said just a minute ago that if the question is asking us about what the water pressure is at the bottom of a tank or at some kind of elevation, we're trying to figure how many pounds per square inch is based off of the head of water above that gauge. So now the things to watch out for in something like this is if the tank is 130 feet tall, but it's only filled when it reaches 121 feet, we certainly don't need the total height of the tank. We only need the water elevation. That's why we used 121 feet here. So there's a couple ways you can calculate this out. And I think I have some examples here that we're going to work out, but you can work this out several different ways. This is feet and this is feet, and 0.433 is PSI per 1 foot of water elevation. So we have an example here. It says the level indicator has broken on an elevated water storage tank, and now we have a pressure gauge reading showing 38.6 PSI. So in this particular case, we're saying that the level indicator is not working, so the level indicator being right here. So we have this older photo here with an old water tank showing the old empty and full gauge on the side. So we're trying to figure out now, based off of the pounds per square inch gauge reading, what the feet of elevation are based on that. So now we're going to use the 2.31 feet per PSI as a multiplication factor, or we can use the 0.433 in the case in the function of a division. So you take the 38.6 PSI and multiplying it by the 2.31. I know it's written out there for you, but 2.31 is the feet of water above that gauge. So 2.31 feet of PSI gives us what? Let's see what we got. 38.6 times 2.31. I come up with 80 9.166, and this would be feet of water. Or we can do 38.6 divided by 0.433 feet per PSI. And let's see what we got. So 38.6 divided by 0.433. And I come up with 89.145. So we got a slightly different numbers, but the actual elevation being 89.1, 89.2 feet of elevation is pretty darn close. So yeah, that's it. That's how we would work that calculation out. Oops, I went the wrong way. Sorry. All right. Let's try another one. I think we have another example. How many pounds per square inch should the gauge be reading if the water level is at 112.5 feet? So let's just say down in this little well house down here, we've got a pressure gauge and it's kind of coming off of that location there. So what would the PSI be reading if the water elevation is at 112.5 feet? Remember one thing about this, one concept I want to share with you about this is that it's not about the actual liquid volume, that's above the gauge. It's not really about how big around this, this diameter is. It has really nothing to do with that. It's just the water column. If you think about a square tube, that's 1 inch square tube, and it's really, really tall, how many feet of water would be in that square tube? So in this case, we're saying 112 feet of water in there. So what would the pressure gauge be reading at the bottom of that square tube? So how we would do this then is if we know we have 112 feet, 112.5 feet, and we want the we want to know the pressure gauge reading. So we are going to use 2.31 in this case. We're going to divide by 2.31 feet per PSI. So 112.5 divided by 2.31. Oops, I hit 2.34 by accident. 112.5 divided by 2.31. And I came up with 48.7 PSI. That's how you'd use the division and the 2.31. If you wanted to use the multiplication factor of the 0.433, it would look like this: 112.5 times, this is feet, by the way, times 0.433 feet per PSI. And what do we get for this? 112.5 times 0.433, and I get 48.7 PSI. So there we go. So we came up with the same units on this one. 48.7 PSI. So it checks out. Guess we did all right. I hope that was helpful. I think it kind of got messed up a little bit there on the beginning of my description, but I hope that that kind of helped out. Let's take a look at another example. Feet of head loss. So the feet of head loss is essentially saying like you're losing pressure. And we're going to equate that to amount of feet by using a couple of these conversions like we just did. But how we lose pressure or have head loss is things like friction in the pipes, the pipe friction, or think about the pipe smoothness. A brand new piece of pipe would be really, really smooth, where say a corroded piece of iron pipe may have a lot of tuberculation and it might be very rough. So pipe friction makes a difference. The length of the pipe, how far we're moving the water, miles or however far, and the actual diameter itself. So all those things go into the head loss. Fittings that are on the pipe, such as elbows, valves, joints, couplings, pressure reducing valves, altitude valves, all that kind of stuff that may be in the water system lines would cause potential head loss. Water meters, You know, we mentioned about meters having, you got to turn a disc to get an actual reading on a water meter. So that does have some head loss to it. So we're going to talk about how to calculate feet of head loss. So here's a question. It says, figuring head loss in feet. If a pressure gauge is reading 80 PSI at the water plant and a pressure gauge on the water main is reading 72.5 PSI at a point 2 miles away, what is the amount of head loss as feet? So we want the actual foot units, not the difference in the PSI, but we do need to know the difference in the PSI so we can calculate the feet of head loss. So first things first is take the 80 PSI and subtract off the 72.5. So I got 7.5 PSI difference. So we lost 7.5 PSI. So when I populate my slide here, it just went right over top of that. So let's go back to this. So 7.5 PSI loss, which we know is good. The next thing we do is convert the PSI into feet by using the 2.31 feet of head per PSI. So 7.5 multiplied by 2.31, and I get 17.3. I got 17.325 on my calculator, but we rounded, just really it's just going up to the tenths on this is fine. So 17.325 feet of head loss was experienced in this pressure differential. And the 17.3 feet of head loss can be because of friction in the pipe, valves that are in the line. We have elbows, things like that, 45 degrees, 90 degrees, you know, all those different turns and twists that we have in the water line. All right, let's try another one. Figuring pressure loss as PSI is another thing that we might want to, talk about. If a pressure gauge is reading 60 PSI at the water plant and the engineer reports there are approximately 19 feet of head loss in the system, then what is the theoretical system pressure? So we're going to kind of figure out what the system pressure is based on a known head loss that we're given. So we have the pressure gauge reading, which we don't need quite yet, but what we need to do is convert the feet of head loss into pressure. So 19 feet of head loss, and in this case, I'm showing using the 0.433 PSI per foot, is 19 times 0.433. I get 8.227, and I'm going to guess that we probably just put 8.3 in this one, and we did. We just used 8.3 for this example. So let me erase that. So we have 8.3 PSI difference or PSI loss. And now the 60 PSI, which is what we have at the plant, and we're going to subtract out the 8.3 differential. So 60 minus the 8.3, I came up with 51. Let's see what we have on our slide here. We have 51.7, and that's what I got on my calculator. 51.7 PSI is the theoretical PSI in the water system based off of that head loss. So we can kind of use this in different avenues. And it says the engineer calculated that there's approximately 19 feet of head loss. That's because we know the size of the reducing valves or reducing like couplings or reducing pieces that are in there, adapters. We have tuberculated pipe. We have things with some roughness to it. We have some length of pipe, how many miles long this is. All that kind of stuff goes into calculating the amount of head loss in the system. So this would give us an idea that if we're at 60 psi and we lost 8.3 psi just from the friction and all of those different things, we would end up with a psi down around 51.7 psi. So that's how you would do that. So we're going to move into flow rates and flow velocity. And we're going to be using a couple of the different calculations found on page 4 of the formula sheets. We're going to be talking about flow rate as cubic feet per second. We're going to be working with another one of the pie charts over here where you see Q and V and A. So anytime you see the letter Q, that stands for flow rate. That's an engineering term to show the quantity of the flow of water moving through a line. And the V is velocity. Anytime you see V, velocity is going to be expressed as either feet per second or feet per minute. And then A in our example here represents area. Area is always known as square feet, which is something we did a little bit earlier in our discussions in this video. So what you notice here in the formula, in the first formula, if I can point to this one, is that we come up with a value of cubic feet per second based on the area, the cross-sectional area of a pipe, multiplied by the velocity that we are given or that we measure in a pipeline. So the formula is essentially velocity times area is going to give me the flow rate. Now, remember, flow rate as cubic feet per second is not the same as gallons per minute. We may have some conversion work to do, like we did in our discussion earlier when we were talking about how cubic feet per second times this ends up being cubic feet per minute. And then it goes to cubic feet per day and all that. We had that discussion earlier in our video session on this series. So we're going to work with a formula like that. You can also see that flow rate in gallons per minute is almost directly given to us here without having to kind of come up with cubic feet per second. It's area in square feet times the velocity in feet per second, which is similar. And then the conversion, here's the conversion, 7.48 gallons per cubic foot is multiplied in. And then the last conversion is the 60 seconds per minute. So this is going to go from cubic feet per second to gallons per second, all the way to gallons per minute. So it's written out just as you see here, all multiplied together. I think the trickiest thing about all of this is to kind of imagine what's really happening in this pipeline when we have cubic feet of water moving through a line. Then we have to convert that cubic feet into gallons, and that gives us gallons per minute or gallons per second. So we're going to work on a couple of these. I'm kind of excited to show you some of these flow rates and velocities and all, because it sounds really kind of scary and it's a little exotic, you know, but it's not really that hard. It's actually pretty straightforward when you just imagine in your mind what we're having happen through these pipelines. All right, let's go dive into this. So the first one we're going to talk about, first one we're going to talk about is velocity feet per second. So we have a couple of calculations. Velocity in feet per second can be expressed one of two ways. It could be the flow rate as cubic feet per second divided by the area, or it could be the distance in feet that a particle has traveled through a water line divided by the time that it took to get a certain distance. So either way, we're going to come up with feet per second. And I'm showing a lot of photos here of hydrants flushing and operators doing this kind of work, because that's where it really comes into play. A lot of times we're talking about water movement with regards to flushing the water mains. We're trying to achieve a certain flow rate or a certain flushing velocity is important. And that's kind of what we're calculating here. So let's look at the first example. The first example says, calculate the velocity in feet per second if small particles travel inside the water main, travel the length of the pipe in 2 minutes. The pipe is 150 feet long and it's 2 feet in diameter. So the first thing we're going to do is recognize which formula will work for this. We had a pipeline, if I go back to the picture, we had a pipeline that was 150 feet long, 2 feet in diameter, and we're given the time that it took for these particles to travel. So let's look at the formula or the potential formulas. You'll notice that there's two formulas we could use: flow rate as cubic feet per second divided by the area in square feet, or we can do distance in feet divided by time in seconds. So the one that fits the best for this example right now is the second formula. It's distance in feet, which we said was 150, divided by the time in seconds. Now, I think we got time in minutes. I think it said, if we go back and look, I think it said it took 2 minutes for it to travel. So we don't have this in seconds, but we certainly do have it in the minute units. Now, so we didn't actually get a cubic feet per second number to use. That's why I'm showing you this formula here. All right, so let's work it out. We're going to convert the minutes into seconds. So we said it was 2 minutes, right? So 2 minutes multiplied by 60 seconds in 1 minute is going to give us 120 total seconds. So 60 times 2 is 120 seconds. That's the time it took to go down the pipe. Now we look at our formula. The velocity in feet per second is 150 feet that we traveled divided by 120 seconds, which is going to give us feet per second. So my calculator, I've got 150 divided by 120, and I come up with an answer of 1.25 feet per second. Okay, there we go. 1.25 feet per second, not 125 feet per second, 1.25 feet per second. So that's our velocity example number 1. How about example number 2? We have equation. It even says in the statement, it says it's a little trickier. So obviously this guy's nervous in the picture. It says it's a little trickier, especially if the flow rate is given as gallons per minute, not cubic feet per second. And if the inside diameter of the pipe is given, not the area. So how are we going to do this? How are we going to figure out the feet per second with some units that are not of the right, shape or size? We're going to have to do some calculations first to kind of get this into the right units and make sure that we're matching everything up, because if we're given gallons per minute, we can use this formula, but we actually have to kind of figure some of this stuff out. All right, so here's what we're going to do. It's called flushing velocity, feet per second, and here's our data. We have a pipe inside diameter of 8 inches. We have a flow rate as 500 gallons per minute, and we know that 1 cubic foot can contain 7.48 gallons per cubic foot. So remember, we're using this formula, which I just circled, and it showed up circled on the slide. And the first step we're going to do, step number 1, is going to be to convert the gallons per minute into cubic feet per minute. Now, how are we going to do that? We know that the gallons per minute is 500 GPM. It's moving through the line at 500 GPM. To convert that into cubic feet per minute, we're now going to do a kind of a reverse calculation using the 7.48, because we know there's 7.48 gallons per cubic foot. So what we need to do then is figure out how many cubic feet per minute we're dealing with. So all we're going to do is it shows here as 500 gallons per minute divided by 7.48 gallons per cubic foot. So in your calculator, 500 GPM, divide that by 7.48. And now what I've got on my calculator, let's see if it populates on the slide. It does. So 66.85. I came up with 66.8449. But again, we're gonna round, and we're gonna say now the flow rate is now converted into cubic feet per minute, because we use the 7.48 to kind of back calculate to what that is as cubic feet. All right. So the answer we're looking for, by the way, is in feet per second. And right now we're in cubic feet per minute. So we're not quite in the right units yet. Let's go ahead and convert the cubic feet per minute into cubic feet per second. So we have our 66.85 cubic feet per minute. And we know that there are 60 seconds in 1 minute. So let's go ahead and divide that out. Now, what we're going to end up happening is the minutes will cancel out, and we'll be left with cubic feet per second. If you wanted to kind of see how we got to the cubic feet per minute in the above example, or the slide above it, or the bullet point above it, we have gallons here and we have gallons here, and they cancel out, and we're left with minutes and cubic feet. So it's cubic feet per minute. So now on the second step, we're going to be left with cubic feet per second. So 66.85, let's divide that by 60. And now I have 1.114 something. We're going to call this CFS. And I'm going to bet that we have it populating on the slide here. Yep, we sure do. So let's go ahead and let me erase what I put here. And the slide then has 1.11 cubic feet per second showing. So looks like we're doing pretty good so far. So we've kind of gone in the reverse of the discussion we had in the very beginning of this whole class when I showed you how the conversions multiply and make things bigger. We're actually going the opposite way, and we're dividing to make things smaller because that's the units we're looking for. So 1.11 cubic feet per second is the flow rate from 500 GPM, but we're not done yet because we still need to know this number. We still need to know the area. We don't know the area yet. We know this, but we don't know the area. So how do we figure out area of a pipe? Well, remember what we have to do here is pi r squared, or 0.785 times d squared. So that's our formula for the area of a cross section of a pipe. So the inches are shown for the pipe inside diameter, but not feet. And we need those to be in feet units. So the inches have to go. The 8 inches need to be converted by divided by 12 inches per foot. So 8 divided by 12 is 0.66666. And I'm going to guess that we probably went with 0.67. Let's see what we did here. Yeah, there it is, 0.67. I wasn't too far off, huh? So 8 inches divided by 12 inches per foot is 0.67 feet. So we're not done. That's not the area. That's just the conversion from 8 inches to feet. So now the way we calculate the area of a circle is going to be, you have a choice, 3.14 times radius, or 0.785 times diameter. And here we have these feet is diameter. So I'm going to go with 0.785 in my calculator, 0.785 times diameter, which is 0.67 times 0.67. And I came up with a number. I'm going to write it over here, 0.352. Goes a little bit further than that, but I'm going to call that feet squared. And let's see how close I come up to the next step that tells us. So 0.785 times 0.67 feet times 0.67 feet. And I came up with 0.35. This is what we have on our slide, 0.35 square feet. So the surface area of this, I'm going to put area of the pipe, equals 0.35 feet squared. Remember, it started off as a 8-inch diameter pipe. So do we have everything we need now? Let's take a look. We've got area here, 0.35, and we've got cubic feet per second, 1.11 cubic feet per second. We have everything we need to actually work the math the rest of the way. So now we're going to go ahead and plug our numbers in. Let's erase this. And let's say now we can go ahead and put our numbers in place. Cubic feet per second divided by the area. So 1.11 cubic feet per second divided by 0.35. And I have a velocity as feet per second showing us 3.17. I'm going to write that down over here, just a kind of little side note here. And let's see what we have on our slide if we're close. So the next thing is divide the cubic feet per second by square feet, and ta-da, there we go, 3.17 feet per second. So why is this important? Well, first off, it's worth a point on an exam. 1 point question, it's worth a point. If it's a 2 point question, it's worth 2 points. So that's obvious there that it's important for that. But the other thing is to know when we're flushing water lines, we want a certain flushing velocity. So we're actually scouring the pipe at the right amount. We actually don't want to just waste our time and waste water without really accomplishing a goal. So flushing water lines at usually 3 feet per second or so is generally accepted, that we're actually moving a lot of water through there and kind of scouring the lines a little bit to flush things out. If we're doing what's called unidirectional flushing, then we might even be higher than 3.17 feet per second. We might go to a nominal velocity of 5 feet per second in some cases. So that's why this is important, to be able to show that we're flushing the lines at the right velocities and actually accomplishing what we set out to do. We don't want to just waste our time, and we certainly don't want to waste the water, because this is going to be unaccounted for water. We're not going to be able to bill for it, so we don't want to waste too much water either. All right, so we had 3.17 feet. So here's one that we're going to try out, and I'm going to write this in each step like we just did. And we're going to work this one out, and I hope that you guys will work this out. You can pause the video here and stop right here and see what you guys get. And I'm going to go ahead and continue on. So we'll work it out, and then I'll show you the answer at the end, because it says I can click for the answer if I want to. So first off, let's do a couple conversions here. So we're trying to come up with cubic feet per second and the area in square feet, and we have all the data we need to do this. The pipe inside diameter is 6 inches. 6 inches is not really what we want. We need this to be in feet units. So let's divide 6 inches by 12 inches per foot. 6 divided by 12 is equivalent to 0.5 feet. So my diameter now is 0.5 feet. My flow rate is 650 gallons per minute. The flow rate is shown as GPM, but it's not cubic feet per second. So let's go ahead and convert the the gallons per minute into cubic feet per second. So 600, let's work this out over here, 650 GPM. And remember, we're going backwards. We need these numbers to get smaller because we're working towards individual little cubic feet per second. So 650 gallons per minute, let's divide that by 60 seconds per minute, and we're going to get gallons per second. So 650, divide this by 60, and I get 10.83. And my units now are going to be, let's see, minutes cancel out. I'm left with gallons per second. Now that doesn't get us into cubic feet per second, because we haven't done anything yet with the 7.48. Remember, I said there's multiple ways you can come up with the same answer. So we've got gallons per second. Let's go ahead and convert this into cubic feet per second by dividing this by 7.48 gal per cubic foot. And when we're done with this calculation, again, the gallons cross out, and we're left with cubic feet per second. So 10.83 divided by 7.48. And right now I have my calculator showing 1.44786. How about we go to 1.45? We'll round off a little bit here, and we'll say 1.45. And what are my units now? It's cubic feet per second. So CFS. All right, so we've got cubic feet per second, and that's what we need right here. And we already converted the inside diameter of the pipe from inches to feet, and now we need to do the square footage of the cross-sectional area of the pipe. So let's work that out. How do we do area of a circle? We can do 0.785, multiply that by the diameter in feet, which we got to do this twice now. So 0.5 feet times 0.5 feet. And for surface area, 0.785 times 0.5 times 0.5, I come up with 0.1962 0.25, and because we rounded a little bit on the one above that, and I want to round a little bit on the bottom here, just go out to the second decimal point out. How about we make this be, instead of 0.19, how about we go 0.20? So we're going to round this up, and we're going to use 0.20 square feet. We'll come up pretty darn close to the answer here. So we have square feet and we have cubic feet per second. So we're going to divide the two. So let's rewrite it over here. So we have 1.45 cubic feet per second divide by 0.20 square feet. And we're going to end up with feet per second. So the square feet right here, remember this is two numbers, two foot numbers, and cubed feet is 3 foot numbers. So when we subtract 2 of the foot numbers away from the 3, we end up with just a singular foot. So that's why it's just 1 foot per, as feet per second. So let's go ahead and figure this out. 1.45, divide that by 0.2, and I got 7.25 feet per second. All right, let's see if we got anything close to that. Oops, let me go ahead and erase some of my stuff here on the slide, because I actually had places I could have wrote all this stuff in. And we did all of that work, and let's see what we got. I had we had 7.25 as our final answer here. And it says that we could be between 7 to 7.4 feet per second, depending on how we round it off. So there we go. Let's go ahead and put the numbers in place. Converting gallons per minute to cubic feet per minute was 650 divided by 7.48. This came out to be 86.8, let's say 86.9 cubic feet per minute. You remember, this is one of the other avenues you could take to do this calculation. In the previous example where I worked it out, I did a little bit different in the beginning, but we're going to come out the same. So 86.9 cubic feet per minute, 86.9 cubic feet per minute divided by 60. Let me make sure I got that number in right. I'm using my left hand, so I might have actually hit the number wrong. Divided by 60. All right, so 1.448 or 1.45 cubic feet per second. Now we're going to convert the inches of the inside diameter of the pipe. We said that was 0.5 feet. And I'm plugging the numbers in here. So calculating the pipe area is 0.785 times 0.5 times 0.5. And we said that square footage was 0.20 is the number we used here. And the square footage was 0.2 here. And the cubic feet per second was 1.45. So 1.45 divided by 0.2 came out to be 7.25. There we go. So that's our flushing velocity. That's a pretty fast pace, isn't it? That's a lot of flow rate through that line. So, all right, that's how we do it. Let's talk about the flow rate itself, the actual flow rate of water moving through a line. Like you see coming out of a piece of pipe here, we have water gushing out. So how do we figure out the gallons per minute or the cubic feet per second flow rates? So we're going to use calculations that look like this. We have either cubic feet per second flow rate to come up with CFS, or if the question says, hey, I want you to calculate gallons per minute, well, then the formula would look like this. Now, either one will work, except you have to recognize one is going to be finished off in gallons per minute, and the other one's going to get you to the cubic feet per second. So this formula up here is essentially going to be this and this, and then 7.48 and then 60 seconds per minute. So the formulas are very similar, but you just have to recognize which one to use. And so depending on what you're trying to get, remember Q is flow rate. Q could be cubic feet per second, or it could be gallons per second, or flow could be gallons per minute. Sometimes flow can even be million gallons a day. This depends on what you're trying to get out of the equation. So here's an example. What is the flow rate in gallons per minute of the full flowing pipe if the velocity is 5 feet per second? The pipe is 2,640 feet long and it's 8 inches in diameter. All right, so let's look at this piece of pipe here. We've got a flow rate of 5 feet per second. That means that for every second of time, it's flowing 5 feet. I'm just going to kind of draw up here and say 5 feet. So 5 feet per second. So it's moving through this line at that flow rate. And the pipe is 2,640 feet long, and 8 inch here is 8 inch in diameter. All right, so we've got a little bit of work to do. We got to first figure out, really what we got to first figure out is what is the cubic foot volume of the 8 inch pipe when we're dealing with 5 foot unit, a 5 foot unit. We have 5 feet that are moving in here, so we're just going to use that as our length, and we're not going to worry really about the 2,640 feet. That's essentially half a mile. We don't really need to know that, because really what we're concerned about is the 5 feet units that are moving through here per second. So let's go ahead and calculate this out. Don't forget, we're going to need to convert inches into feet before we can do this. So step one, the velocity is given as 5 feet per second. We know that that's going to be our length of the calculation we're going to use for cubic feet. So convert inches into feet. 8 inches divided by 12 came out to be 0.67. And I agree with that, 0.67 feet. On my calculator, I got 0.66666. And now we're going to calculate the pipe opening, the actual opening of the pipe itself. You know, the what's called the cross-sectional area is going to be the circular formula. So it's 0.785 area of a circle times diameter times diameter. And so let's just make sure that we got what's showing here. I got 0.785 times 0.67 times 0.67. And I do have 0.352 square feet, and this shows 0.35 square feet. So I think that's pretty good. That checks out. So that's the opening of the pipe. And now what we're going to need to do is follow our formula that says feet per second velocity here times the area in square feet is shown here. So we have our feet per second and we have our square footage. So we're going to end up with cubic feet per second. Remember, feet squared is like this, is written like this. Square feet is written like that. And feet per second, there's only 1 foot unit right here. So when we factor them together, we're actually going to end up with 3 foot units, which are going to be the cubed feet per second. So 5 feet per second of water traveling through there at that velocity, 5 feet is going to be 5 times 0.35 surface area. And I come up with 1.75 cubic feet per second. And let's see. Yep, that's what it came out to be. So let me go ahead and erase this so we can see this a little bit clearly on our screen. So yep, I got 1.75 cubic feet per second. So the next step is to convert those cubic feet per second into gallons per second by multiplying by 7.48 gallons per cubic foot. So we've got 1.75 cubic feet per second times 7.48. So 1.75 CFS times 7.48. And now I come up with, I'll write it over here so it's not right in the way, 13.09. And this is going to be gallons per second. And let's see if that's what we have on our slide here. 13.1 gallons per second. So far, so good, right? We're checking it all out. Convert the gallons per second into gallons per minute by multiplying by 60 seconds in a minute. So 13.1 gallons per second times 60. And over here, I'm going to write 786 because I think now this is the gallons per minute. And we had 786 gallons per minute. So there we go. There's our flow rate in gallons per minute. So we started off with a pipe. If I go backwards here for just a second, we started off with a pipe that was right here. We had a pipe that was 5 feet per second velocity, and it was the 8-inch diameter, and we said it was 2,640 feet long. So which piece of information did we not use at all in that calculation? We didn't use the length of the pipe. It doesn't really matter what the length of the pipe is when you're given the velocity as feet per second. The velocity is actually has the length in it that we're really worried about. We're not really care about the whole pipe. We just want to know how many gallons per minute are flowing through here if the velocity is this many feet per second. And it's all calculations that are conversions from one unit to the other. So 7.48 has to be factored in. We have to convert the inches into feet and to come up with square footage. So really the 2640 is erroneous information, doesn't really play a part in this calculation. All right, so there's our tutorial for that one. And we had a practice one here that came up in just a second, which was right here. So it says calculate the gallon per minute flow rate of a 2-inch water main flowing at 3.5 feet per second. And it says we can click for the answer, but I'm not going to show you the answer right yet. Let's work this one out. So it says here, stop the video, try calculating it on your own, and then restart and see how we did. So you can stop right there, and I'll give you all a second to do that. So what's our first step to do? We need to get in gallons per minute, and we're not near that right yet. So I'm going to kind of look at this from a couple of avenues here. First off, we've got this inches unit. Inches will not work for us because we really have to have things in feet units, so we can use the 7.48. We're trying to come up with cubic feet here. So 2 inches, let's do this first. 2 inches divided by 12 inches per foot is going to give me what? So 2 divided by 12. I got 0.1666 and right, and it keeps right on going. So how about we go like this, 0.17. Let's go with 0.17 as our feet. This is now going to be 0.17 feet of diameter. No more inches. Now we're in feet units. So let's go ahead and erase this off of here so we're not confusing this with anything. And next thing we have to do is start thinking about this feet per second and feet of water main diameter, and start converting things. So we have this skinny little pipe or 2-inch water main that's flowing at 3.5 feet per second. So let's just do this. We got a piece of pipe. This is going to be a 2-inch piece of pipe. So this was now it's not 2-inch anymore. It's 0.17 diameter, and it's flowing. Let's say this. Let's say that this is 3.5 feet here, and it's moving through there at that many feet per second. So now what do we need to do? So let's convert, or let's make this be cubic feet per second. So how do we get the surface area of the pipe? We need the surface area. So 0.785, multiply that by the diameter. We said 0.17 times 0.17 is going to give me the area. So 0.785 times 0.17 times 0.17. And for area, I have 0.02 is 0.0226. So how about we go 0.023? And we'll go out that far because that'll kind of keep us a little bit more accurate, especially since it's such a small piece of pipe. So that's our area. That's our cross-sectional area. Now, how do we figure out cubic feet per second? We know that we have 3.5 feet per second. And now we need to figure out cubic feet per second. So 0.023 feet squared multiplied by 3.5 feet per second should give me cubic feet per second. So 0.023 times 3.5 gives me 0.08. And we don't need to go any further than that. This is 0.08 cubic feet per second. All right, so far so good. We want gallons per minute, but we're not really there yet. We're in cubic feet per second. So we need this to be a much larger number because we want GPM. So 0.08 cubic feet per second. Now let's convert this into cubic feet per minute times 60 seconds per minute is going to be what? 0.08 times 60. And now I have 4.8 cubic feet per minute, CFM. That's cubic feet per minute, but that's not gallons per minute. It's just cubic feet per minute. So 4.8 CFM multiplied by our factor of 7.48 gallons per cubic foot. So multiply times 7.48 and 7.48 gal per cubic foot. And remember now cubic feet cross out and we're at gallons per minute. So we're in the right ballpark here. I came up with 35.9 gallons per minute. Come on, gallons per minute. My screen got a little messy there. There we go, gallons per minute. So we should end up with 35.9 gallons per minute of water flow through the main if we are a 2-inch main flowing at 3.5 feet per second. Let's see how we did with our answer. All right, it says we should be between 31 to 36 gallons per minute, depending on rounding. And guess what? We are right there. We are between that. We are right in the right ballpark. And again, depending on rounding, the rounding came in here, here, here. You know, we had some rounding that we did. So we are close. We are really good. This is a great number. If you came up with a number way different than that, then go back and figure out where you missed something. You should be somewhere between 31 to 36 gallons per minute. And that is the gallon per minute flow rate. All right, let's talk about flushing time, the actual time it takes to flush a water main to achieve certain flushing goals. So when we flush water mains, like I mentioned just a little bit ago, we're trying to achieve a certain velocity and water movement through the line. We want to actually like turn over the water so that we're actually displacing or removing the water that's been kind of sitting in the line and bringing fresh water into the line. So we need to remove volumes of water from the pipe and flush that out. So we're going to calculate something known as flushing time in seconds, and then we're going to convert that into minutes so that we know how long to leave a hydrant open at a certain flow rate. So we do have flow meters, flow gauges that we can use on hydrants, and we know about how many GPM or cubic feet per minute a hydrant can do. And we're going to use some of that information to help us calculate the time it's going to take to flush. So let's go ahead and check this out. Got a couple formulas showing here. We got volume of cubic feet divided by the flow rate in cubic feet per second, or you can come over here and it says length of pipe times the number of flushing volumes. Like say you're trying to flush 2 volumes of pipe or 3 volumes of the pipe. And we're going to divide that by the the velocity in feet per second. So there's a couple ways we can do this. It's on the formula sheets, page 5. So the first thing is the question is going to read to us. It says the operator is flushing a 10-inch water main at a velocity of 3.5 feet per second. The distance being flushed is 1,000 feet, and she is required to meet 5 flushing volumes of water. How many minutes should she flush the main? So we're showing here in a picture hydrant which is gushing water up pretty good. So how long should we flush the main to get 5 flushing volumes out of the pipe? So we're going to use the formula that shows the length of the pipe and the number of flushing volumes. So that's our formula of choice for this one. So plugging our numbers in, but we still need to know the velocity, and I think we have that number. We still need to know the amount of feet of pipeline, and we have that number, and we know the flushing volumes. So where does the 10-inch water main fit into this? Actually, it doesn't actually fit into that, does it? We have all the other numbers. The 10-inch doesn't really fit in. It doesn't matter that it's a 10-inch main. So the step number 1 is 1,000 feet to flush times 5 volumes. So 1,000 feet times 5 volumes is 5,000 feet per volume, total that we're going to move. 5,000 feet of water line for all that. And then we're going to divide that number. So we have 5,000 feet of volume. We're going to divide it by the feet per second of flushing velocity. So 5,000, divide that by 3.5. And I come up with 1,000. Well, let's see if we have it coming up on the screen here, because I'm just going to end up having to erase it. So let's do this. And we're going to come up with 1,429. And that's what I have on my calculator. I got 1,428.57. So we're going to round a little bit here. So 1,429 seconds. So how long is that going to be in minutes, or if it's in hours, depending on what they want to know. So how many minutes, they're asking us here, should she flush the main? So we're in seconds right now. So we got to convert the seconds to minutes. So 1,429 seconds, divide that by 60 seconds per minute. And I'm coming up with 23.8. This is what answer I have. 23.8 minutes. And I would say that just round that up to 24, and you will have moved the right amount of water volumes through that water main at 3.5 feet per second. So that's how many minutes we would flush. Pretty straightforward. So that concludes part 4 of 7. And I hope that was helpful and not too confusing. If you have any questions, remember you can always write me or ask questions through email, and I'll be glad to help you guys out. So we're going to take a quick break, and we'll start into part 5 here just shortly. Thank you. Okay, we're back. We'll talk about part 5 of the water distribution system math. This is going to be all about the pumps and pumping math, total dynamic head, and talking about the motor horsepower, water horsepower, wire to water efficiency. So that's kind of where we're going with this part of our discussion today. So let's jump in here. So the first thing is to calculate the total dynamic head, or TDH, of a pump system. So to calculate the TDH, you must first calculate something known as the static head in feet. So if you look at the formula that we have for TDH, for total dynamic head in feet, the formula reads like this. It's the static head in feet. That's when it's sitting, when the pump is just sitting, not moving, and the water's not moving. Static head is sitting still. So it's going to be the lift, how much it has to lift, or if it's got to suck the water up, and then the pressure or the head against the water moving through the line. So static head has to be calculated. And then to do the rest of the total dynamic head, we would calculate in friction loss. And we're given that through the engineers with the knowledge of, say, the valves and the elbows and the roughness of the pipe and all that fun stuff. So the formula for total dynamic head actually incorporates the static head along with it. And the formulas are shown on the formula sheet. That's page 6 of the formula sheet. So let's go ahead and try one out and see how we do with this. You'll probably find it's pretty straightforward. It's mostly just all addition of these numbers together to come up with a total number of feet that is represented by the head or what we're pumping against, or the extra work that the pump has to do to kind of get this water moving through the pipeline or to discharge at a certain point. So here we have some pump data, and we have a suction lift, which is 15 feet. So we're pumping, say, out of a clear well. And we have a discharge head of 200 feet. After the pump, we're going to go through some valves, and we're going to go uphill and maybe discharge into a ground storage tank or elevated tank or something. And we know that the friction loss is roughly 45 feet of total friction loss through the line. So to do this, the first thing we need to do is calculate the static head. So to come up with total dynamic head, we're going to first use the suction, or rather the static head first. So static head is going to be the 15 feet of suction lift here. And we're going to add that. Notice it says suction lift plus the discharge head, which is 200 feet. So that's here. So we're adding these two together. So 15 feet plus 200 feet is essentially 215 feet. So that's the static head. The second part of the formula reads like this. The total dynamic head is the static head plus the friction loss that was given. So we're going to add together the 215 with the 45, and we're going to come up with total dynamic head. So 215 plus 45, I came up with 260 total feet of head that we're working against in the pipeline. So total dynamic head is a pretty straightforward calculation. There's not really a whole lot to it. It is something that I think distribution system operators should be familiar with, because it's something that we do recognize in the industry as something that is necessary when we're calculating flow rates and water that's needed to come to a certain point, and how much it'll take for us to move that water through there. So let's try this one out. We have an example here. So we have 4 choices. Notice over here we have some multiple choice questions. So you have several different numbers to pick from. And let's see how we do. So we said that the formula for TDH, total dynamic head, equals the static head. And this is feet, plus the friction loss, LOSS, sorry, that's kind of messy, isn't it? So the friction loss, that's terrible, in feet. So the friction loss as feet. So let's plug our numbers in. Suction, static head, we know is the suction lift. So static head is going to be the suction lift, which is 22 feet, plus the discharge head, which is 187 feet. So let's do that calculation. So 22 plus 187. And I get 209. And now we're going to add to the 209, we're going to add the total friction loss, which is 195 plus 195. And what do we get? 209 plus 195. I came up with 404 feet of TDH. So what answer looks the best? Is it A, B, C, or D? Looks to me like B is the most correct answer. So there we go. That's how we're going to do that calculation. Out of all the stuff that we're working on here together in this video series, that's probably one of the more straightforward, simplified calculations we'd have to do. Hopefully, that's a pretty straightforward one that you guys can do without too much of an issue here. Just adding mostly all together. So, all right, let's move on to the next one. Let's talk about horsepower. This is a little bit more intricate. We have a little bit more stuff to kind of factor in here as far as the values go. So you're going to notice on these, there's some very close similarities. You'll notice that the numerator part, the top part of the formula on all three of these is the same. Notice that the flow gallons per minute is multiplied by the head in feet on all three of these. What really changes is the denominator side, the bottom part. That's what changes. And that's where we start factoring in the efficiency of the pump or the efficiency of the motor and the pump together. Because we're using a motor and a pump to actually move water through a pipeline. The water horsepower is essentially just the horsepower it would take to just move water through the pipe without actually adding in or combining into this the inefficiencies of the pump and or the motor with it. So the 3960, you notice 3960 in all of these. 3960 is a constant. You don't have to worry about where that really comes from. Just know that it's a constant that's used in all of these calculations. It's the result of dividing 33,000 foot-pounds per minute by 8.34 pounds per gallon. And that really comes back into play when we're talking about the kind of in the olden days, talking about how they calculated energy and energy needed to move things. And we used horses a lot. So how much power did a horse have to exert to move water for us? And if we use an example like what I'll show you here on the next slide, you'll see this value. So this is showing that horsepower is equivalent to 33,000 foot-pounds per minute. So 1 horsepower is equivalent to 33,000 foot-pounds per minute. So you could word it like this. You could say that 1 horse could pull 330 pounds 100 feet high in 1 minute. That's one way to look at it. Or you can say that 1 horse can pull, or let's say the power of 1 horse can pull 1,000 pounds up 33 feet in 1 minute. So that's what they're showing here in this example. Is this second one is the power of 1 horse can pull 1,000 pounds 33 feet in 1 minute. It would take the horse 1 minute to do that. So that's the equivalent that we're coming up with the 33,000 foot-pounds per minute. And again, that's where the final number of 3960 is coming from. So we're not going to worry too much about that from this point on. We're just going to know that 3960 is a constant. So water horsepower is the horsepower required to lift water at the discharge of the pump. Brake horsepower is the power applied by a pump into the water to be moving, and the water it has to be moved with a pump that's not 100% efficient. Pumps generally have a little bit of slippage inside, especially as they wear. They don't put out nearly as much GPM as they get older as they do when they're newer, or they've had rebuilds done on like the impellers and wear rings are replaced. So this is measured at the pump input shaft where the brake horsepower is. And then finally, the motor horsepower is the power required by a motor to turn the pump, which has to then move the water. So all of these things go kind of hand in hand together. If we look at this example I have on this slide, if we have a clear well, the clear well is actually holding water in it, and we need to get it up or to a place that's higher elevation, or we're pumping against head in feet. Let's say that we're pumping across town into a ground storage tank from the clear well at the plant. So we're pumping against head in feet, which is essentially the valves, the elbows, and all that fun stuff that we talked about a little bit earlier. So if we were just going to move water magically without any pump or motor, then we would just have to know water horsepower. But we are having to use pumps and motors that are not 100% efficient, and we're going to factor in these inefficiencies when we come up with our final answer. So just looking at this picture, that black line from the clear well to the ground storage tank is essentially the same thing as saying water horsepower that would be needed by the pump to move that water, just without even being an inefficient pump, just to move the water itself. but we're having to go this way. We're having to go this direction. We got to go through a pump and then into the storage tank. So we got to move water with some pressure through these lines and get volume moving through so we can fill the ground storage tank. So we're going to use a motor that's not 100% efficient. There's efficiency loss here, and there's efficiency loss here using percentages of an inefficiency with these pumps and motors. So brake horsepower is essentially measured there at the shaft of the pump. And the motor horsepower is the motor horsepower needed to move the pump that has the brake horsepower, which is also factoring in the water horsepower. So there's kind of a hand-in-hand symbiotic relationship going on between these. So let's take a look. First one is water horsepower. The water horsepower, again, is just the liquid movement. So we have the flow rate as gallons per minute multiplied by the head and feet, that it's actually moving against, and we're going to divide that by 3960. The second calculation is known as brake horsepower. Brake horsepower is, again, the flow rate needed, the necessary flow rate as gallons per minute times the head and feet. And here's the 3960 again, but notice it's multiplied by the efficiency of the pump written as a decimal point. So pumps, like I said earlier, they're not 100% efficient right out of the, even as brand new, because the impellers have a little bit of slippage or leakage around the impeller when this thing is turning. So there's some inefficiency kind of built into these, and especially as they get older, they get a little bit more inefficient as age happens, and we start pumping abrasive materials. So that efficiency percent needs to be written as a decimal point. So it's going to be point something something something. And motor horsepower then is, again, the flow in gallons per minute and the head and feet, which we talked about earlier, divided by the factor of 3960 times the pump efficiency as a decimal, and then the motor efficiency as a decimal. So it's several different calculations done for this. So let's take a look and let's try one of these out and see what we get. So suppose you need to pump a certain GPM of gallon per minute flow rate into a certain process. How big should the pump be to meet that flow rate? And then how big should the motor be to turn the pump and move the water? So we have to kind of factor in these different things so we can get the right motor and the right pump to move the water. So here we have an example. So it says calculate the water horsepower, the pump brake horsepower, and the motor horsepower for the given situation. So we have three different things that they would like us to do, or that we would like to get out of this. So the first things first is the water horsepower. So I'm just going to I'm going to use this side of the board or screen here to write the formulas out, and then we'll jot the numbers down. So first off, water horsepower is going to be like this. It's going to be the flow rate in gallons per minute, which is 700 gallons per minute. And that's going to be multiplied by the head and feet that we're pumping against. Remember, it's the elevation difference, it's the friction in the pipe, the length of the pipe, the valves, the elbows, all those types of things. So 400 feet. So is going to go right here. That's going to be multiplied together, and we're going to divide that by 3960, which was our constant factor of the 33,000 divided by 8.34. So let's work this out. So 700 GPM times 400. So this comes out to be 280,000. Divide that by 3960 is going to give me my water horsepower. So divide by 3960. And now for water horsepower, I got 70.7 water HP, water horsepower, 70.7 water horsepower. So I'm going to jot that number down. How about we put our numbers up here? 70.7 as the WHP. I'm just jotting them down up here so we don't lose track of those. All right, so let's erase this so we have some room to work. We've got that part done. The next thing we're going to do is the brake horsepower. The question is asking us to do three different horsepowers. The next one is the brake horsepower. So brake horsepower is going to be the required GPM, 700 gallons per minute. This is almost the same as what we just had a second ago written up here. I just erased it. And that's going to be divided by 3960. But the 3960 has to be multiplied by the pump efficiency as a decimal point. So here's the pump efficiency is showing 80%. Remember that 80% needs to be converted to a decimal. So it will be 80 divided by 100 gives me 0.8. So it's going to be written up here as this: 3960 times 0.80. That's the equivalent of 80%. So go back to our calculation. So the 700 times 400 was again the 280,000. And then we're going to divide that by 3960 times 0.8. So my new denominator is 3168. So we have everything kind of written out now. Let's go ahead and do our final answer or final division. 280,000. Divide that by 3168. So for BHP, for brake horsepower, the pump needs to have the ability for 88 point, let's round that up and say 88.4 BHP, brake horsepower. So 88.4 is the BHP. So up here, I'm going to put BHP equals 88.4. All right, so we got two of them done so far. And here's what I want to do and kind of maybe expedite this a little bit. Remember that all three formulas use the same numerator, which is the top part. So remember, we don't actually have to do a whole bunch of extra work here to do the last one, the motor horsepower. We can keep the 700 gallons per minute is multiplied by 400 feet. So that comes out to be 280,000. So that can stay. What about the denominator? What has to be done on the denominator? Well, that's going to be a separate number. It's going to look like this. We had 3960. We multiplied for the pump part of the efficiency was 0.8. Just a second ago, we had that as the pump efficiency, 0.80. But now we have to factor in the motor efficiency. It says here the motor efficiency is 75%. Remember, writing that as a decimal would equal 0.75. So let's put that here, 0.75. So now let's do our numerator, or rather our denominator. Let's figure out what the new denominator should be. So 3960 times 0.8 times 0.75. So multiply all those. And now for the denominator, I get 2,376. So that is my new denominator. So we can just go ahead and finish out this math. I had 280,000. Divide that by 2376. And now I have a motor horsepower requirement of 117.84. Let's just go 117.8 motor horsepower. So up here, I'm going to put MHP because I think my answers are going to come up here shortly, but I want to kind of see how good we did on this. 117.8 for motor horsepower. All right, so we came up with three different answers. Notice that as we went down the list here, that the horsepower requirements got greater as the units became less efficient. So if you have a motor that's only 75% efficient, it really needs to be equivalent of 117 or almost 118 horsepower just to keep the gallons per minute flow rate what it should be, because we're pumping against 400 feet of total head. So you can kind of see how this is easily getting much larger as far as horsepower goes because of inefficiencies or things in the pipeline. If you want to go to a smaller motor and save some money, maybe if you can change some of the pipeline features to not be such a amount of head and feet that you're pumping against, maybe use smoother pipe or maybe have less elbows or whatever, shorter run. And if you can put a higher efficiency motor in place and rebuild your pump to get it a little bit more efficient, you may save yourself a lot of money because you're having to run this inefficient motor a lot of hours to meet this this requirement. That's kind of how this factors is into the actual budgetary process for overall costs. So let me go ahead and erase some of the stuff on the slide here, and let's take a look and see how we did on this. Let's take a look at our answers. I don't want to have this stuff in the way. So let's go back and click our button here and think and see how we did. So the first thing is the water horsepower shows as 70.7 HP. So we did good there. That one looks pretty good. And the brake horsepower, 88.4, that's good. And last one was the motor horsepower, 117.8. All three of those checked out pretty good. We are right in line with what the answer should be. So congratulations, you figured out horsepower, brake horsepower, and motor horsepower. A lot of times people say, I'm never going to use this in the industry, thinking maybe I'm never going to see this or never need it. I have had experiences in the industry where this would have been great information for me to use to save a bunch of money on my electric bill. And I could have recouped those costs and save the utility a lot of money. So next thing is to apply it into an efficiency of how well is the energy from the motor being converted into work being done by the actual pump. So let's look at this from another avenue with the numbers that we just did. We're going to kind of use those into another calculation to show the efficiency as percent. So what we need for this is the actual water horsepower. That's just the horsepower to move the water through the pipe. And then the motor horsepower, which we said was somewhat inefficient. Let's see how efficient this is as a calculation goes. This gives us an indication of how efficient we're putting that energy to work, and then recovering those costs or spending the money on the electric bill, because that's where the real costs goes, is in electricity. So the bottom part of the calculation is either going to be the brake horsepower from the pump or the motor horsepower. It tells you that, or they asks you that in the question, or based on the information given about the actual scenario. So here we are, we're going to look at the motor horsepower for this example. So to figure the wire to water efficiency, you got to calculate two separate horsepower values. You have to first do the water horsepower, and then we are going to calculate the motor horsepower. So we have some information showing here. Let's calculate the wire to water efficiency. We've got the pumping head. We've got the flow rate necessary. Remember, that's a part of each of these calculations. We've got the pump efficiency, the motor efficiency, which we need for the motor horsepower. And then they gave us the pump impeller size. Now, back in the calculations that we just did, where did you see us using the pump impeller size in the calculations? And if you're thinking for a second, we didn't use that, did we? I don't remember us using that. Sometimes there's extra information in these and we don't really need it in this calculation. So let's not get confused on what's necessary and what's not necessary. So first off, let's do this water horsepower as WHP. So here we have our example. So we said we had part one, the wire to water efficiency part one. We had 1,400 gallons a minute that was necessary. And we were pumping against 220 feet of head, right? Let's go back and check. Yep, 1440. Okay, good. So let's do this calculation. So 1,400 times 220 gives me this. I've got 308,000. So 308,000. And let's go ahead and divide that by 3960. And now let's see what our water horsepower is. So 308,000 divided by 3960. So I came up with 77.7. And in some cases, they probably would just go ahead and round up to 78%, would probably be okay. And here we have that number, 78% right there. So that's good. And let's go to, I'm sorry, that's 78. It's not percent in this case, it's just 78 horsepower. That's not percent, I'm sorry. Erase that. Must be getting late in the day because I'm getting tired, huh? All right, so 78 horsepower. So what about the motor horsepower? Notice that the numerator is the same on this, so we can use the 308,000, and then we're going to divide by the factor of 3960 times 0.84 times 0.87. Those are the pump efficiencies, and the motor efficiencies written as a decimal. So let's go ahead and do that. So 3960 times 0.84 times 0.87. And for the denominator, I got 2,893.968. So I'm going to leave that number just the way it is, and we'll do our rounding here and see what we get. So the motor horsepower is 308,000 divided by 2,893.968. And I've got a motor horsepower. Looks like I got 106. Let's see what the answer is showing here. Here we go, 106. There's our motor horsepower. So that checks out good. So far, so good. Looks like we got everything we need. So let's go to part number 2 for the wire to water efficiency. We've got our two numbers, and now let's plug them in. So you see here where it says wire to water efficiency is water horsepower divided by motor horsepower, and then multiplied by 100 to move the decimal point for our percentage number. So we're going to have the number's going to look like this: 78 divided by 106. So 78 was the water horsepower, divided by 106 for the motor horsepower. That comes out to be 0.7358. And then when we multiply by 100, we move the decimal point a couple places over. So my final answer should be 73.6, and we report that as percent. So what do we have as our final answer? Well, we're showing 74%. That looks pretty good to me. 74%, 73.6, round it up. We are 74% efficient wire to water efficiency. That's how we do that. So I hope that was helpful. This concludes part 5, and we're getting ready to start part 6, which is more administrative math. And then we're going to be closer to be wrapping up, and you guys will have everything you need. I hope this has been helpful so far. So I'm going to give my voice a rest, use the restroom. I'm going to take a break. I'll see you guys back in a few minutes. All right, let's get into part 6 of the water distribution system math. This is going to be the administrative side of things. And we're going to talk about water loss. We're going to talk about things like this water leak right here, and unaccounted for water, and percentages of pieces of equipment that we have on site, and some of those types of things that go into the administrative and accounting side of the mathematics. For those of you, again, going for, let's say, higher level licenses, you may see more questions like this on exams that would pertain to some of the supervision and management side of things. Maybe this might fit into more of the reporting to the water management districts. This might go into budgeting and things like that. So that's what we're going to spend a little bit of time on. So let's go ahead and get into it. So accounting and administrative mathematics. So we have a few things to talk about first. We have a formula shown as gallons versus the population served. So what we're going to figure out from this is gallons per capita per day. How many gallons of water are being used per person per day? So per capita is essentially, the amount of water that a person uses in a day. So they basically say that we use somewhere between 100 to 150 gallons per person per day. And if you're in a place where you're conserving water, it would be much less than that, maybe 50 to 100 gallons per person per day, or maybe even less than that if you're, ultra conservative on water. So the things we're going to calculate from this is going to either be gallons used per person per day, or even the population that's served based on some knowledge of what each person uses per day. So we can calculate a couple of things from this. The first thing is, let's calculate the gallons per person or per capita per day. So the formula looks like, as you see here, it's gallons per capita per day is equivalent to the volume of water produced in gallons per day divided by the population served. So it's a pretty straightforward calculation. We just need to know a little bit about our population. The census can give us that, or sometimes your city records can help you with that. But we have an example here. It says a small water system pumps 725,000 gallons per day from its wells, the groundwater wells. The population served is 5,800 people. What is the gallons per capita per day? So this sounds a lot like the town that I live in, as far as how many gallons are pumped, and the amount of people that we have in our small town is around 5,800 people. So we're going to put the numbers in just as you see. Now, when we talked about converting gallons to million gallons earlier in this video series, we talked about making sure that we have the right units, like for pounds per day. We calculated gallons and then we converted it into million gallons. In this particular case, notice that the units that they want this to be in are gallons per day. So we don't want the MGD or million gallons. We want the actual gallons per day factor. So that's okay for this one. We've got that number shown right there. So the volume of water produced is 725,000 gallons per day. And we're going to divide that by the population, which is 5,800 people. So we're just going to say persons, people, whatever you want to put there. So 725,000 gallons per day divided by 5,800. And I come up with 125 gallons per person per day. Gallons per capita per day. 125 gallons per person per day. That's how we work that one out. The population served can be also figured if we know something about the amount of water that a person uses per day, or the average usage. So we just turned this calculation around a little bit. We have the same numbers, but maybe we want to figure out what the actual population is. So in this case, we can estimate, or we can use an estimation of, say, 125 gallons per person per day. And if we know that we're pumping 725,000 gallons out of the wells, then what's the population? So in this particular case, we're not going to use this exact formula, because that was the formula we used just a second ago to figure the opposite. This one is, we have 725,000 gallons per day, and we're trying to figure out the people. So we would divide this by 125 gallons per person per day. And we're going to end up with persons as our final answer. So this is a little bit different than what's shown up on the top of the slide. We're just kind of reworking this formula a little bit. So 725,000 gallons per day, divide that by 125 gallons per person per day. And guess what we end up with? 5,800 people. So that would be our estimated population. So that's how we would work some of this stuff out with kind of a administrative side of things. Since there's no direct formula for this one, if we wanted to figure it out, like I said, we just kind of have to figure out, just turn the math around, and that's what we just did. So this is kind of the tutorial on that. We know that there's 125 gallons per person per day, and the population is known as the per capita. So capita, we'll say, was the C part, and it shows like this. And we end up with, we said, 5,800 people. That's basically it. So try another one. A water plant pumps 56.5 million gallons a day into its water distribution system. The per capita usage is 125 gallons per person per day. Or gallons per person per day. So what is the population served? So we have 56.5 MGD. Remember what the formula is. The formula wants us to have this in gallons per day. So we actually need all of the digits, all of the zeros back in place. So 56.5 MGD. And now we need to actually multiply by 1 million. I know in the past calculations, we've been dividing by a million to get it into gallons, or rather get gallons into million gallons, but now we're doing the opposite. So 56.5 times 1 million. So I come up with an answer that looks like this. I have 56,500,000 gallons per day. So that's my flow rate out of the water plant per day. And if we know that each person on average uses 125 gallons per day per person, then the gallons per day will cancel out at the end and we'll end up with just persons. So 56,500,000 divided by 125. And we come up with a population of 452,000 people. And there you go. So 452,000 people would be using, if they're using 125 gallons per person per day, we would need to supply from our water plant 56,500,000 gallons a day. So looks like letter B, answer B might be our best choice for this one. And let's see if that's what the answer comes out to be. Yep, there it is. So we did pretty good. All right, so far so good, I hope. Let's talk about averages and percentages. So averages is also known as the arithmetic mean, or the middle of the road, like the average. It's not the high, it's not the low, it's kind of the average. So let's talk about what that is. It's the it's calculated by the sum of all the terms or measurements divided by the number of terms or measurements. So what does that mean? That sounds crazy, to terms and measurements. So averaging is essentially adding all the numbers given, let's say over the course of a month. We have all these flow numbers for the whole month. And then we divide that answer, that sum of the addition of all of those, by the total number of values that went in. So if you're looking at a 30-day month, then you put 30 numbers in, you added 30 numbers together, and you divide your answer by 30, which is going to give us the average per day. So averaging is pretty straightforward, but let's make sure that we're all clear on how to do this. So here's an average flows for a week of a water plant. So what do we have here? What would the average be for the week? So you see numbers that are anywhere from, say, 1,356 all the way up to 2,365. These are all gallon figures. So all we really need to do here is add the 7 numbers together. And I'm going to go ahead and do that. And hopefully you guys are doing the same thing already. So 1548 plus 1875 plus 1789 plus 1356 plus 1478 plus 2365 plus 2045. And for the sum of all of these, I got 12,456 gallons. This is total. That's the total that was pumped for the week. And if I want the average daily flow for that particular week, I'm going to now divide this number by the total number of numbers I put in. So let's say I have 1, 2, 3, 4, 5, 6, 7. So divide by 7, and my average daily flow, ADF, for that week is 1,779.4 gallons per day. So the average flow for that plant is 1,779.4 gallons per day. That's average flow. And how did we do? Whoops. And we came up with that number, and that looks pretty good. We're right on track. So averaging is something that you may see in your workplace that you have to do. Sometimes it's averaging a whole month's worth of numbers. Sometimes it's averaging a yearly amount, like how many pounds were used on average at a water plant. If you're using so many pounds per month, you would have to add those up for the year. So 12 months worth of data added up, divide that number by 12, because there's 12 months, would give you the average monthly usage. So there's some different applications for this in the industry. And a lot of this does kind of go back into the budgeting for fiscal years and things like that. So that's where we kind of see this more for reporting purposes and budgeting purposes. Let's talk about percentages. This one is used in a couple of avenues to talk about like percents of good meters that we have, or how many meters would we be changing out if we're going to change out 10% of a total number of meters. Let's say per year we have a goal of a meter change out program of say 10% of our meters per year. And if you have certain number of total meters, how many meters would you be changing out? So that's where the percentages come in place. I'm going to use an example here to give us an example to start with. Let's say that we have a semi truck on our grounds that we have to talk about tire replacement. Let's say we're going to replace a couple of tires per month, and what percentage of tires are being replaced. So a semi truck has 18 tires. So you can kind of see in this picture, we have kind of the 18 wheel semi sitting here without the actual, the actual body of the vehicle. We just got the 18 tires. So 2 of the tires are worn out and need replaced. So let's say this tire is worn out and needs replaced. And let's say this tire back here is worn out and needs replaced. What percentage of tires will need to be replaced? So how we're going to do this is we're going to take the 18 is the total number of tires, right? So I was having a little brain fart there for a second. So we have 18 tires, and we need to replace 2. So 2 divided by 18. 2 divided by 18 is 0.11111 as a decimal. And what is that as percent? We multiply this by 100%, and that gives us times 100 gives us 11.1% of the tires need to be changed out. So if you weren't sure if that was a correct number and you're like, it doesn't sound right. Well, if we have 18 tires, let's just say 18 tires we have on the truck, and let's say half of the 18 tires need to be replaced. So what is half of 18? We know half of 18 is 9. So let's say that we have 9 tires that need to be replaced. So that's 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 9 tires out of 18 total. 9 divided by 18 gives us 0.5, and multiply that by 100 gives us 50% of the tires. So if you were trying to see if the number made sense and you weren't really sure by looking at it, the number you have on your calculator, and you're thinking maybe you multiplied it wrong or divided it wrong, then you can kind of work it out and say, well, what do I know and how would this look if I was to do it this way? So in this case, we had 50% of the tires that need to be replaced if 9 of them were bad. So this also does kind of fall into, let's say you have valves on your plant grounds at your warehouse or in your yard, and you want to know how many of the valves are good or how many of the valves are bad or whatever you want to know from this, what percentages are needed. So here's an example. We have an inventory of gate valves in the warehouse. And out of the 110 valves that we have, 16 were found defective. So we had 16 defective valves hanging around at the warehouse. And out of the 110 valves we had, what percent of them were considered defective? So 16 bad valves divided by the 110 total. So the 110 is the value that we know we have. And then we're going to divide it into or divide it by the 16. So 16 divided by 110. And then we're going to multiply this by 100 to get the decimal point in the right spot. So 16 divided by 110 times 100. And I come up with 14.5%. We show up here that 0.145 is the intermediate number. And then by multiplying by 100, we come up to 14.5% of the valves were bad. So that's how we calculate percentages with relation to, say, valves and things like that. Let's work out one more of these. Let's say we have a water system that collected 85 coliform samples in a month. 6 of the samples came back with positive results. What percent of the coliform samples were positive? So we collected total of 85 samples, right? So that's 85 samples, and we want to figure out what percent were positive. So out of the 85, 6 came back positive. We're going to just put a plus here, positive. So 6 divided by 85 gives me, this is going to give me 6 divided by 85 is 0.07. And we multiply this by 100 to move the decimal point over, and we get 7.05% were positive. So 7% of the monthly samples were positive. By the way, that wouldn't be a good thing because we can't have more than 5% come back positive over the month, because we're trying to make sure that we're putting out good water and we're actually protecting the public health. And if you're collecting more than 40 samples in a month, you're allowed up to 5% to be positive, but it looks like we're over that. So we're going to have to figure out what's happening in our water system if we have coliform samples, like you see a coliform dish here with some total coliform growing on there. That's those little silver little specks on there. All right, so we ended up with 7% of the monthly samples were positive. All right, I'm going to ask you one more question here. We're going to kind of word one more of these, and I'm going to work one with you because I think I want to make sure we're clear on something like meters and meter changeouts. So earlier I said that what if we have a total number of meters, water meters in a system, and we want to, let's see, put here total water meters. And let's say that we have service connections in town, and we're going to say residential meters, not commercial meters or anything like that. So the total residential water meters is going to equal, how about we have 2,880 residential water meters. And we want to change these out on a meter change out program, and we're going to change out 10% a year. So how many would be changed out if we're doing 10% change out per year? So how many would we be changing out? So we're going to take 2,000 that's an 880 So I'm just making sure I'm going to have the right number here. So we have 2,880 total meters, and we want to figure 10% of those. So what is essentially 10% of 2,880? All we have to do with this one is multiply this by the percent written as a decimal. So 10% is written as a decimal like this, 0.10. So 2,880 times 0.1 is going to give me 288. So out of a year, we should change out 288 meters for a yearly change out of 10%. So I just wanted to kind of point that out, that may be something that you also want to be able to factor. So 10% is kind of a good number that you see in industries and in utilities as a meter change out, because they do get old after a while. They do slow down. They usually don't register the same as they get older. So we kind of factor this into our budgets, and we say we're going to change out so many meters per year. And we just kind of do that as a constant thing. All right, so I just wanted to kind of point that out. There was one more that I don't think I had on the presentation, so I just thought I'd share that with you guys. All right, so let's go back to more accounting math. The water utility produces a very valuable product. Remember, what we're doing is making a product, and we're selling this product. It's very important that we account for the water that's being used by our citizens and what we've pumped out of the ground or we've made in our water treatment plants and pumped into the water distribution system at the point of entry in. So usually there's a bulk meter or some kind of metering system to say how many gallons came out of the ground or through our water treatment plant total and into the water distribution system. So the utility hopes to account for all of the water produced and provided to its customers. Wouldn't that be great if we knew where 100% of our water went? But that's not usually the case. We actually have things like leaks, we have flushing, we have firefighting, we have water theft in some cases where people are hooking to a hydrant and taking it unbeknownst to us. So that's something we got to factor in. It's called water loss. So what we're going to try to do here is talk about what the percentage of water loss is. So a 0% amount of water loss is really not a reality. We almost can't account for 100% of the water pumped and treated and sent out and accounted for, because we have meter inaccuracies and all that stuff. So there's always an amount of water that's not accounted for. I will be honest that 20 to 30% water loss is not uncommon, although it's not very good because we're losing money and we're actually using more water than we're accounting for. We call that percent unaccounted for water, and the consumptive use that we have the permitted for by the water management districts may actually prohibit us from being too high on water loss. So we would say in this that if you could get down to less than 10%, that would be wonderful. And in some cases, water utilities have gotten it down less than 5%, and they've been able to account for almost 95% of the water produced and used. So that's wonderful. If you can get down less than 5%, you're doing something, I think, really, really special. Okay, so percent water loss. Let's look at some of this. We have a water utility pumping a monthly total of 23 million gallons from its wells across the whole month. It bills its customers for 17.9 million of that water. So 17.9 million was what we billed for. So what's the percent of water loss? So we're going to go and we're going to figure this out. So we have 23 million gallons pumped, 17.9 billed for, and we want to know the water loss. So the formula shows like this. Here's unaccounted for water percent. The water produced, gallons, subtracted from the water billed, gallons, divided again by the water produced. So it's essentially the in minus out divided by in as like an efficiency goes. So let's do this. Let's take our 23 million gallons pumped minus the water build gallons. Now we're using million gallons on both of these. So as long as our units are equal, we should be good to go. You wouldn't want to have gallons in one unit and million gallons in the other, but everything right now is million gallons. So we're equal here on units, so we can keep those the same. So in is 23 million gallons that we put into the system, and we accounted for 17.9 million gallons. And you're going to see that this is in parentheses, like we talked about earlier, PEMDAS. Remember, please excuse my dear Aunt Sally, all the way from our beginning discussion. And then we're going to divide that by the water produced, which is 23 million gallons again. And that whole thing then is multiplied by 100 again to get the decimal point in the correct spot as a percentage. So let's go ahead and work this out. So 23 million subtract 17.9. And I'm going to rewrite it down here at the bottom. So I got 5.1, and then we're going to divide it by 23 million. This 5.1 is million gallon difference. This is million gallon difference. And the 23 million gallons is the total pumped. So 5.1 divided by 23 gives me 0.2217, and we multiply this by 100, gives me a decimal point, moves over to 22 point, let's say 17 or 22.2% unaccounted for water. Let's see how we did on this. Oh, we didn't have that as a worksheet with an answer. So this is the actual answer. I thought maybe we had it written out with an extra answer coming up, but that is the unaccounted for water for that question. So 22.2%. So we can try to get that down better and try to make sure that we're accounting for the water build. Again, where does water go that we're not billing for? Leaks are a big one. Water theft is possibly another one. Firefighting that we're not accounting for fighting the fires, and for hydrant flushing and automatic flushing to keep water fresh sometimes is unaccounted for. We should really try to keep as best account as we can so we can reduce the amount of water loss. All right, let's try another one. A small utility is pumping a total of 0.856 million gallons in 1 month from its wells, and it sends bills to its customers that account for 748,000 gallons. What is the percent of water loss? So here we have an example of gallons units and million gallon units. So what you need to do is figure out what is more comfortable for you to put into the calculation. Both units have to be alike. So if you're going to say work with the million gallon units, then the gallon units here have to be converted to million gallons. So let's take a look at that. So 748,000 gal is divided by 1 million, which we talked about quite a bit here today. So 748,000 divided by 1 million to get it in million gallon units. We have 0.748 million gallons. So we can work with that, and it's a little bit easier to handle because we don't have as many zeros. So why don't we do that? Let's do our math then. So it's the in number, or the volume pumped, which is 0.856, subtract from that 0.748, and notice again that's in parentheses, divide that by the number that we started with, the actual numbers pumped, so 0.856, and these are all million gallon units, by the way. So I'm going to put here million gallons, so we know we're working in million gallon units, and then multiply it by 100%. So let's go ahead and work this out. So 0.856 subtract 0.748, and this comes out to be 0.108 million gallon difference, and divide that by 0.856 million gallons gives me what number? So 0.108 divided by 0.856, and I get the number that looks like this. I get a 0.126. And now we're going to come down here so we have room to work. 0.126 times 100 is going to move my decimal point 2 places over, and I get 12.6% water loss. So not too bad, less than 20%, not quite down to the 12%. So that's how we work out the percent water loss. All right, so there's our numbers, and we had the worksheet here to do that. And remember what I just said, we had million gallons here, but gallons, and we converted the gallons into mg to work this one out. Just watch out and make sure that all the units are alike. All right, and we have this picture from the Associated Press several years ago of a water hydrant that had been struck in Los Angeles, and the person is kind of thinking, how do I account for all this? You know, wow, there's some water gushing out on the ground. Nobody's been kind of accounting for it. It's just coming out. How many gallons is that going to be? So how do I account for that? I don't know. That's a good question. You'd kind of have to know what the flow rate is through that water main and all that fun stuff. All right. Utilities bill customers set on an amount that they use. Utilities have different rate structure set up. So we have, like for residential, we have certain number of gallons cost this much money, and then anything over that we charge more. So there's different rate structure set up, but we're going to kind of talk about how much a water bill would be broken into its individual components. So we know, like per this many gallons is this, and per that many gallons is that. So the gallons used over the initial amount is charged more or at a higher rate. So if a customer uses 17,000 gallons of water per month, let's just use this example. So 17,000 gallons of water per month. And the billing rate for this water is $1.90 per 1,000 gallons for the first 10,000 gallons. So anything up to 10,000 gallons is $1.90 per 1,000. And then over that, the structure is set up so that anything over the 10,000 gallons up to 20,000 gallons is billed at $2.15 per 1,000 gallons. So you kind of see some differences here on how this is going to work out. So we have 17,000 gallons total. We know that the person or the folks are going to be charged a certain number per the first 10,000, and then we have to add into that the higher rate for what's the difference. So let's take a look. So to calculate the cost for the first 10,000 gallons, what we generally do is take these gallon units and break them into 1,000-gallon components. So we know that for each 1,000 gallons, we're going to charge $1.90. So if we say that we have so many units of 1,000 gallons at $1.90, and we divide the total 10,000 into this, we can figure out how many units and how much that base rate will cost. So if we have 10,000 gallons and we know that we're basing everything on 1,000-gallon units, let's figure out how many units of 1,000 gallons we have. So 10,000 divided by 1,000 gallons per unit is going to be 10 units. On my calculator, I've got 10 units that equal 1,000 gallons apiece. So far, so good. We've got 10 of those units at 1,000 gallons apiece. Each unit costs $1.90. So we have 10 units at $1.90 per 1,000. So now we're going to multiply 10 units times $1.90 times 1.90, and we come out with $19. So it's $19 for 10,000 gal. Okay. And so far, if we use exactly 10,000 gallons a month, and that's our rate structure, then we're going to pay $19 a month. But now we know that it's actually more than that. We used, I think, 17,000. So we're going to have to figure out what that difference is, the higher rate. So let's go to the next page, and we're going to calculate the cost for the leftover 7,000 gallons because we're in between the 10,000 and 20,000 gallon range. And so that is going to be, I think, was $2.15 per thousand. So 7,000 gallons divided by 1,000 gallon units, we're coming up with units of 1,000 gallons apiece. So 7,000 divided by 1,000 gives me 7. So I have 7 units of 1,000 gallons apiece. So the rate structure then is 7 units times $2.15 for each one of those units. So 7 times $2.15, I come up with $15.05. So for the 7,000 gallons that was over the base number of 10,000 is going to be charged at $15.05. Now what we need to do is add the two together, add the two sums together to get the total amount. So 19,000 is for the base rate, and the 1505 is for the 7,000 gallons that was over the base rate. And so $19 plus 15.05, and I came up with $34.05 per month. So that would be our water bill for that month based on the 2-tier billing rate structure. Pretty straightforward. Yeah, it takes a little bit of practice to kind of get used to these, how this stuff works. But as you do it a couple times, you start figuring it out and kind of see how this stuff fits in. So let's see. So we've got this lady, she's got a headache, and that maybe you do too by this point. If you've been listening to this video all day long, you probably have a headache too. So utilities lose money annually just because we have inaccurate meters. I mean, it's just a part of the nature of the beast. That's why we do meter change outs, and we do like 10% of the meter change outs per year. And it's interesting that when you guys probably know this, but I'll just share this with you, that when people complain about a high water bill, they usually think that the meter's turning too fast because it's an old meter, but the opposite is really true. They usually turn slower, and we start to lose revenue. And so we change out this old meter and put in a new meter, and then their bill goes up even more. So it's kind of a phenomena that many of us are aware of as the utilities managers and supervisors and clerks and billing clerks and all that. So utilities lose money annually from inaccurate water meters. And what we can do is estimate the annual revenue lost based on an average meter inaccuracy. So if we figure that so many meters are so much percent inaccurate, we could figure out our loss. So it's called lost revenue per year. If a small utility pumps 46 million gallons in a year, so a whole year, 46 million gallons, and they build an average of $1.75 per 1,000 gallons, and the estimated meter inaccuracy is 10%. So the meter inaccuracy is 10% on an average. How much revenue is lost per year? So we can kind of figure this out. We know we have 46 million gallons, and we know that we're billing an average of $1.75 for each 1,000 gallons. And we know that the meter is inaccurate, on an average about 10%. We're losing money. So how do we do this? Well, first got to break the total amount of water into those 1,000 gallon units. So let's do that first. We took 46 million and we broke it into gallons. So 46 million or a million mg is now written as 46 million gallons. As you see here, we just multiplied by the number 1 million. So we take the 46 million that we pumped per year and divide that by 1,000 gallon units. So divide by 1,000, and we come up with 46,000 units that are 1,000 gallons apiece. So 46,000 units of 1,000 gallons each. Okay. The next thing we're going to do is multiply this by the number or the dollars per 1,000 gallon unit. So we're going to figure out what we would be recouping if we were charging $1.75 per unit. So 46,000 units of $1.75 a piece. So 46,000 times 1.75, and you come up with $80,500 per year at 46,000 units at $1.75 per unit. We have billed or tried to recoup $80,500 per year. But we know that 10% inaccuracy is hurting us. So how much money is the 10% inaccuracy actually costing us? So 80,500 is what we should have got, but there's 10% inaccuracy. Remember, 10%, like you see written here, it has to be expressed as a decimal, which is 0.10. So 80,500 times 0.1 gives me $8,050 per year of revenue that's lost because of 10% inaccuracy. So $8,050 lost per year. That could be a lot of money to a small utility. All right, so that concludes part 6. That's the administrative side of things. I hope that was helpful. And we're going to take a quick break. I'm going to stretch out again. And I know that you guys are probably just watching this right back to back, so the breaks seem kind of weird to have, but go ahead and stretch and, relax your brain for a few seconds. We'll stop the video here and I'll see you on the other side. Okay, welcome back. And here we go into the last part of our water distribution system mathematics. I hope this has been helpful for you all, and that you're enjoying it and getting something out of it, and being patient with me. And sometimes I'm going a little slower than others, but it's been a good series of videos, or this video is hopefully a good series for you to study and help you get ready for your exams, and also for just operation of the water facilities, and just in general. So we're going to do the last part. The water distribution system math is just the miscellaneous. And this is where I've put the temperature conversions. And that's really all we have in this section. So it's temperature conversions going from Fahrenheit to centigrade, or centigrade to Fahrenheit. And we'll go ahead and work these out. So here we go. Let's have some fun with this, like our friend here in the picture. All right. So what about water loss? We talked about water loss a few seconds ago. Here's a hydrant, and it looks like somebody's got the hydrant open and they're spraying their buddy with cold water. Probably a fun thing to do on a hot afternoon in the city, which looks like what's happening. But man, as a water operator, you're thinking, what about all that water loss? We didn't account for all this water. So we just talked about that a few seconds ago in this segment, in this video series. All right, let's get into temperature conversions. So there may be a time when you have to convert from centigrade to Fahrenheit, or Fahrenheit to centigrade, either way, back and forth, using a calculator. And let's go ahead and work it out. So the first thing is we're going to convert from degrees Fahrenheit, and we're going to get into degrees Celsius. First things I want to mention to you is that degrees Fahrenheit, the actual number that we're dealing with, is most always a larger number than the degrees Celsius. There is a point where there's an equivalent, but we're not going to worry about that. But for purposes of what we're doing here, the degrees Fahrenheit is going to be a larger number than degrees Celsius. So say, for instance, we have degrees Fahrenheit of, let's say, water boils, at a degrees Fahrenheit of about 212 degrees Fahrenheit. And that equivalent for degrees Celsius is 100 degrees C. So you can kind of see from this quick description that at 100 degrees Celsius, we have 212 degrees Fahrenheit, and it's really essentially the boiling point of water, at sea level and regular barometric pressure and all that fun stuff. So let's just kind of work a couple of these out. I think we have an example coming up, and we'll show you this. Now, there's two formulas here to come up with degrees Celsius. The first one shows, in parentheses, we have degrees Fahrenheit minus 32. So we would do parentheses first and then multiply by 0.555. Or you have another choice of the division method here, which shows degrees Fahrenheit minus 32 as your numerator, and then divide that by 1.8. So either way, parentheses comes first, and you do the subtraction. So let's try one. So let's convert a temperature of 95 degrees Fahrenheit into degrees Celsius. Remember that degrees C is always going to be a number lower than degrees Fahrenheit. So the first thing we're going to do is subtract the parentheses and then divide to get the correct answer. So let's see what we got here. Degrees Celsius is going to be, we had 95 degrees Fahrenheit, right? So let's try 95 degrees Fahrenheit. And let's do the parentheses first here. So it's minus 32. And we got that in parentheses. And then for the first example, we have multiply by 0.555. And that's going to give us some number. So 95 degrees, subtract 32. And for this product, I get 63. So it's going to be 63 times 0.555. And I come up with 34.965 degrees C. And there's another formula showing here. Let's work that one out. And let's try that. So it's 95 degrees Fahrenheit, subtract 32. Remember, that's in parentheses. So we're going to do that first. And then that product will be divided by 1.8. So there's just a conversion factors here. So 95 minus 32, again, that was 63. Divide 63 by 1.8. And I get, right on the money, I get 35 as an exact answer. So it's 35 degrees C. Either way you do this would be considered accurate. Notice that the first method had 34.9, which essentially then you would round up to 35 anyway. So both of these should give us 35 degrees Celsius. And by the way, that's usually what the incubators are set at for the total coliform sample that we do in a laboratory. So incubators for total coliform are usually around 35 degrees Celsius. All right, let's do another one where we're converting the Celsius into the Fahrenheit degrees. And this one only has one formula showing for us. So we're just going to follow what's given here. And it shows that we're going to do the multiplication first. It's in parentheses, but I guess it probably doesn't have to be because we're working using PEMDAS or working from left to right. It still will come out the same. So let's work this one out. Degrees Celsius is going to be a lower number than degrees Fahrenheit. So our final answer should be much higher than what we started with. So when we're doing this one, to get a larger number, we use functions like multiplication and addition to have a larger result at the end. And do anything in parentheses first. So how about we do a temperature conversion of degrees Celsius into degrees Fahrenheit? Let's work that one out. So here's our formula. So we had 20 degrees C, and we're going to multiply by 1.8, and that's in parentheses, which means do that first, but we already know that. And let's work this out. So 20 times 1.8 multiplied by 1.8. So this comes out to be 36. The product there is 36. And we're going to add 32 to it. So 36 plus 32. And I came up with a final answer here of 68 degrees Fahrenheit. So 68 degrees Fahrenheit is greater than the 20 degrees C. So that is correct because it's going to be higher than degrees Celsius, but they are actually equivalent. So if you're using degrees C or degrees Fahrenheit, you have an equivalency there. So that's how you work those out. Degrees Celsius for laboratory, there's certain incubators that are used in laboratories that we use environmental samples, and 20 degrees Celsius is a common incubator temperature. So that concludes this video series on water distribution system math. I hope you're not feeling too much like this guy, and I hope you're not feeling too much like this guy that you're saying, I don't get it, I don't know what to do. I hope this was helpful. That's our goal here. And I hope that this is kind of what you're saying, like, oh, this isn't as bad as I thought it was going to be. You know, I can do this. This math is doable. So if you have any questions or you need more clarification, or if it looks like I did something incorrect and you want to check me out on it, I have no problem. Thank you for doing that. If you have any questions or anything, please call me or write me and include the slide number. Like you see down here, this is slide number 202 or 202. Include the slide number and the equation that you're talking about, whatever it is, so that I can kind of have an idea, go back into the presentation and say, okay, this is what we need help with. And I'm really, really happy to do that. I hope that I have been helpful to you, and that this video series will help you study for your exam and use this stuff in the field, whether you're billing or painting a pipe or putting chemicals in a tank. This is designed hopefully to help you solve those math problems. So again, my name is Ron. My number here is 352-294-3881. Please call me, leave me a message. If I'm teaching class, obviously I won't be able to answer the phone, but I'll get back to you as soon as I can. You can also email me. This one works really well. That's usually a good way to catch me even in off hours. So rtrigar@trio.ufl.edu is the best email for me. So I hope that it's been helpful, and maybe we'll see you on the next video, and take care, everybody.